So it's nice to begin the year with you here, and here in this very warm city. So our conference is actually this Black Hole and Gate Theory Holographic Enlightenment is actually a conference we are supposed to think of as some kind of liaison with the University of Amsterdam, University of Southampton, Stag Research Center. Sorry, because somehow when I saw Kostas, I saw Amsterdam, sorry. So he was in, so University of Southampton, where we have the Stag Research Center, which is sort of has the same kind of philosophy like our Center for Strings, Gravitation, and Cosmology, where we focus on various, from astrophysics to even fundamental quantum gravity to observational cosmology to real theoretical cosmology, and of course string theory and various aspects of understanding quantum black holes and all. So we we hope that we will have this seminar series twice every year, or roughly of that frequency, where we can have a back and forth exchange between our research scholars and all this. So this conference has been supported very much by the Dean of Global Engagement, Professor Raghunathan Rangaswamy, who is chairing this amazing initiative, and he's the one who has got your visa letters and made our visas happen, and all this. So there is a dedicated conference center which helps with all these facilities, as you see, and which has made this organization of such things possible, and also getting the approvals from various ministries and all. So it is so it's very so I invite Professor Raghunathan to say a few words about these facilities and IIT Madras also.
Thank you, and welcome to IIT Madras. I see some differences already. I see the speaker in very casual clothes, which is fantastic to see compared to the other ones I have inaugurated. As Ayan said, at IIT Madras we have a dedicated conference secretariat now, with the idea of getting lots of conferences here at IIT Madras. Last December, we had about, I think, 12 to 13 international conferences, large scale, here at IIT Madras. And by the way, Ayan, all the money comes from IIT Madras, nothing from me, or the dean. So I've been called for many inaugurations. I almost joked that my December was inauguration month, no other work month. But I'm very happy to be here. Welcome, Kostas, to this wonderful campus. For people who are new to IIT Madras, just a few words about IIT Madras, and I'll let the conference proceed. This is a beautiful, about 600 acres campus with multiple animals. You would have seen deer and so on. As far as the institute itself is concerned, the institute has been around for 60 years now. And I would say predominantly the first 40 years, the institute was heavily focused on undergraduate education. It was the most premier and continues to be the premier undergraduate education center in India. Of course, you know, 1 in 100 get into this institute and so on. All of that has created a buzz around the institute. But what I just wanted to focus on is that in the last 20 years, all IITs in general have focused more on research. So we have become more research intensive in terms of our focus, while undergrads still are in some sense our flagship, because they are very visible. They are the CEOs of big corporations all over the world and so on. We are very proud of our graduate programs, and we are very proud of our departments doing excellent research work. Just to give you some idea of the composition of the campus, we have about 10,000 students now. 3,000 are undergraduates, 3,000 are PhD students, and 4,000 are postgraduate. So about 70% postgraduate students. We have about 600 faculty, so that tells you that roughly every faculty has about 5 PhD students working with them. So that makes up for this excellent research environment that we currently have. And the reason for this conference secretariat was that when you have so many graduate students, it's incumbent upon us to bring the best in the world to come and talk to them, so that they learn from all of these interactions. And I'm really pleased that you are here, and the students and the people here will benefit from this workshop conference. This workshop is on black holes, gate theories, and holographic enlightenment. I don't think even if I stay here the whole day, I'll get any enlightenment about the topic. But I am sure you can because of your background, and I hope that you have a fantastic time at IIT Madras, and you will think about visiting us again if you're from outside. Thank you very much, and all success to the conference. Thank you.
The first speaker would be Kostas, and he will talk about holography of QFTs in De Sitter.
Okay, so first I'd like to start by thanking Ayan and Suresh for organizing this. This is the second work in the series that organized together between Southampton and Chennai, and I hope it will continue in the future. There is another common thing between Southampton and Chennai, as I recognized yesterday. You can see here the deer. That's why we call the center stag, because historically in the forest a lot of deer, and there are lots of deer here as well. So there's another common feature. Okay, so what I will discuss today is about how to use holography to understand quantum field theories in De Sitter. So, okay, here we are. So the plan of the talk is I'll start with a general introduction, why this is an interesting topic, and then I will move on to discuss some basic stuff about the conformal boundary of ADS and what is the meaning of boundary metric or conformal structure. And then this is going to be the natural point where we're going to start discussing quantum field theory in De Sitter using holography in ADS. That will be the bulk of the talk, and then I will discuss a toy model for quantum field theory in discussion, namely free massive fermions in De Sitter, and then I will conclude. Okay, so let's start with the introduction. So the physics of quantum fields in De Sitter is important for many reasons. First, we know that we live in a universe with a positive cosmological constant, and therefore even the very basic stuff, a kind of the standard model, we need to understand standard model physics in De Sitter. And we also believe that the very early universe underwent a period of exponential expansion, which is the inflationary period, where the description is again well approximated by quasi-De Sitter. So if you want to discuss cosmological observables, then usually these are well approximated by quantum field theory in a fixed De Sitter background if one is interested in slower order inflation. And this was one of the reasons, this kind of two items, why people back in the beginning of 80s, one started discussing quantum field theory in De Sitter. But it turned out that actually the subject is quite complicated. So weakly coupled quantum field theories in a fixed De Sitter background is a topic that has been studied and revisited roughly every 10 years. And roughly every 10 years, people discover many subtleties, and they go back to the same kind of stumbling blocks. In particular, it has been well known that you have light fields where the mass is much less than the Hubble constant. Then there are severe infrared divergences at loop order. These are first discovered actually even before this famous paper by Starobinsky in the late 70s. And the meaning and the implications of those has been debated again and again. And here I put some names, but there are a lot more. And again, roughly every 10 years, people revisit the topic and they find the same issues. So if you want to understand the issues, clearly one needs a different perspective, because the same tools have been tried and studied year after year, and people go back to the same subtleties. So this was the motivation for this work. Now we have holography, which gives a different angle a topic, you can, instead of studying a weakly coupled quantum field theory, now you can study a strongly coupled quantum field theory and try to understand some of these issues. Do you still have strong infrared divergences? Okay. So this talk will be based on a paper I wrote with Jose Benin, who is actually in the postdoc market, and Ben Withers. We have one paper out, and there is still an ongoing work as well. And there is also some relevant earlier work that we used from Alex Bushel. So before I move on, I want to also emphasize that this work is conceptually distinct from the topic of de Sitter CFT and holographic cosmology. And I think later on next week I will give another talk about holographic cosmology. But just to distinguish kind of between the two, so in de Sitter CFT, the aim of the game is to try to describe a de Sitter universe where you have kind of dynamical gravity in terms of some d-dimensional conformal field theory without gravity. So here we're not going to do this. Instead, gravity will be fixed. So we're going to describe quantum field theory on a fixed gravitational background, which we choose to be de Sitter. And holography will now be in the bulk. So in this context, in a sense, the dual theory is the CFT, and then the dynamics produces a quantum gravitational de Sitter universe. In the work that I'm going to describe here, the de Sitter is on the boundary, in a sense that I will try to make clear in the next few slides, and then holography happens in the bulk. So we're going to use gravity in ADS in order to describe strongly coupled quantum field theory on de Sitter. Okay, so that's the motivation. So I need questions on the motivation. Say it again. The QFT will be on the boundary, and this we're gonna describe. I will spend a lot of slides explaining exactly how to make sense of that. Yeah, so it would be gravity would be weakly coupled in the bulk in ADS, and would be strongly coupled on the boundary. So in the usual sense of holography. So usually we have, let's say ADS 5 crosses 5. When ADS 5 is weakly coupled, then any cosmos superunion mills would be strongly coupled. So here we're going to have the analogous statement here would be that we're going to have a quantum field theory, a strongly coupled quantum field theory on de Sitter, and this will have a description in terms of ADS in one dimension higher. Yes, any other question? Okay, so let's start from the beginning. So now we're going to go back to basics. So there are a lot of common misconceptions about the conformal boundary of ADS. So I want to start a little bit slower and try to uncover those, because this becomes very important when you try to put on the boundary de Sitter rather than, let's say, flat space. So quite often what one finds in the literature is the following statement. So you try to find coordinates so that the metric looks in this way. And then one says that the boundary is at r equal to 0, and then this metric here is the boundary metric. Okay, this has appeared in hundreds of papers. So in general, this statement is not correct. And it's not correct because usually when people write down the metric in this format, the coordinates, the boundary coordinates x, are non-compact. So when the slices, the r equals constant slices, are non-compact, this statement here is not correct. So what is correct is that if you manage to bring the metric to this format, and in addition, the R equals constant slices are compact, then there is a conformal boundary at R equal to 0, and the metric that we have over here is a representative of a boundary conformal structure. And I will explain what these words mean in the next few slides. Time, actually, this is going to come in the next slide, yes. So if you want to have all coordinates including time, you really have to consider time as being compact. But most of the subtleties come not from the time direction, come from the other directions, which are non-compact in most kind of discussions in the literature. So what I want to emphasize is that the conformal boundary does not depend on which coordinates one is using. So quite often, people just change coordinates, and they say, oh, in this coordinates, the boundary looks de Sitter, looks ADS, looks whatever, and then they want to use that property to study properties of quantum field theory on that space. That's not correct. So let's go slowly. So let's start from ADS. So the metric in global coordinates has the form indicated over here. But this R bar coordinate has a range between 0 and pi over 2. So now with these coordinates, then the R equals constant slices are compact. And here, that's the point that we just discussed. So what we usually call ADS in the physics literature is the universal cavalry of ADS. So the time variable in ADS is compact, so I'm going to take tau to be between minus pi and pi. But then the other coordinates, these are just spherical coordinates, or these are all compact. So now, in this case, the conformal boundary of ADS is at tau bar equal to 0. And, and the boundary is the Einstein universe. And I will make this yet more precise in the next slide. So now if you look at this metric, then this metric diverges when R bar goes to 0 because of the 1 over sine square R bar. So this means there is no well-defined boundary metric. This metric here diverges. What is well-defined is a conformal structure, namely a metric up to conformal transformation. Yeah, that I should have put, so here it should have been an S1, which again I uncover. But I mean, the subtleties with uncovering the time, there are no subtleties with going to the universal cover. So most of the subtleties are with, so when one takes the other coordinates, not to be compact. Okay, so okay, let's make this yet a little bit more precise. So since this metric diverges, there is a mathematical procedure. It goes back really to Penrose, but it has been more developed in the mathematics literature. So one starts by using a so-called defining function. And this defining function has the following properties. So it's a function which is positive in the interior of the space and has a single 0 at the boundary. So if you have such a function, then you can multiply your metric with omega square. And then this quantity here now has a limit as R bar goes to 0, because the second order, we have a second order 0 because of omega, and you have a second order pole in G, and the two cancel out. However, if you have one defining function, any other, you can obtain another one by just multiplying with an exponential of a regular function, because if this is positive, then that's positive, and if this has a single 0, that has also a single 0. So it satisfies the defining properties of a defining function. So this means that this procedure here that gave rise to what one might call a boundary metric actually defines a metric up to a Wald transformation, because you can use a different one. So what's canonically defined is a conformal structure. So let's apply now this to the example we're using. So in ADS, you can put W to be sine R bar. So this is in the range of coordinates we're discussing. So when R is between 0 and pi over 2, the sign is positive. N has a single 0, R bar go to 0. And therefore, if I pick this, then this leads to the following representative. So I have, if once I pick a specific defining function, I get a representative of the conformal class. So this metric here, the Einstein universe, is conformally flat. So this means that any other conformally flat metric is as good. So this is not, as you will see in the next slide, you can implement this by changing coordinates. But at this point, what is the boundary of ADS is independent of coordinates. It's just a geometric structure that you have in your space-time. So the, oops. Suppose we didn't have compactness. This means that if you're at some constant R bar place, then there will be another infinity, which is in infinite along the boundary directions. So the true boundary of the space will not be at R bar equal to 0. It would be the collection of R bar equal to 0 plus all the infinite directions in the along the slices. And that's actually how you can actually see it explicitly. If you choose non-compact coordinates, you can always recover, go back, and for example, in the case of ADS, recover the standard boundary of ADS, which is R cross SD. No, in the case of asymptotically ADS spaces, I don't make any choice. No, in Lorentzian. Well, time like infinites are two points in ADS. Well, in the Euclidean case, there's no such choice. In the Lorentzian case, there are also two additional points at time like infinity. Okay, here we are. Now, going from one representative to the other, because we're considering a conformal field theory, this wouldn't make a difference, except that in even dimensions, there is a conformal anomaly, and that means that physics does depend on each representative. So I'm going to suppress this because they're not going to play a role. I'm just going to put it here so that it's clear that there is an effect in even dimensions. Now, in all cases, one can change representative by doing a bulk diffeomorphism. So if you have a conformally flat conformal structure, you can represent this just with a Minkowski metric. This is using Poincaré coordinates. You can represent it with an ADS metric, and then you can use an ADS slicing of ADS, or you can represent it with a de Sitter metric. This uses a de Sitter slicing of ADS, which I'm going to show you in the next slide because it's going to be important in this talk, or more generally by any other conformally flat metric. For instance, you have an FRW metric, and there is an FRW slicing of ADS as well. This does not change what the boundary is. It is well known that all conformally flat metrics are a portion of the Einstein universe. So the boundary is always the Einstein universe. When you choose different coordinates, you describe kind of different patch of the boundary. So different representatives describe the same boundary but in different ways. So since the CFT is invariant under Weyl transformations, then for the purpose of ADS CFT, it really doesn't matter which representative one is using. And again, there have been many papers in the past where people, the only thing they've done is change coordinates and then do a computation. This cannot give you a different answer like with any of these choices. So you have to do something beyond choosing coordinates. Okay. So any questions? Okay. Oops. Okay, so in the cases of, so the de Sitter slicing would be important because you want to study conofil theory in de Sitter. So, and I'm going to give it in the case of ADS4 because this is going to be the application, but it's the same formula in all dimensions. So it has the form indicated over here. So you have a de Sitter 3 metric, you have a prefactor that depends on the Hubble constant, and yeah, this is the metric. So now to see a little bit more explicitly the statements I made in the previous slide. So you can now start from that metric, make this coordinate transformation indicated here. This is going to launch you to ADS and Poincaré coordinates. And you can do a further transformation given over here, and then you'll add in global coordinates. Now, if you want to see which part of your space-time the different coordinates cover, okay, so this is now this is the boundary. So the boundary in this case is R cross S2. So here, this is the time direction, goes from minus pi to pi. And for the S2, we need two coordinates, and I'm going to suppress the azimuthal angle, so there is a circle over the entire space. And okay, this is the Einstein universe. So the de Sitter 3 is conformal to a portion of R cross S2, and this shows which portion it is. So essentially, you have two de Sitter 3 fit into the Einstein universe. So de Sitter, let me go back to the previous slides here. So de Sitter, of course, itself has a second order pole at infinity, so has past infinity and a future infinity. And so this is the past infinity of de Sitter, and this is the future infinity of de Sitter. And then here I wrote it in two different ways. This is the inflationary parts. These are kind of more global coordinates. So the inflation part is this one. And then in terms of so if I define y to be sine t of sine r, then as I go to minus infinity, I go to that region. As I go to plus infinity, I go to that region. So depending on what is, whether, so this is always positive. So depending on whether t is negative or positive, so I get the two different regions. So this is the boundary. So now let's view the same object from the bulk. So now the boundary is really that line over here. So here in this Penrose diagram, every point is an S2, which shrinks to zero size at the origin. And this blue line is the boundary we had over here, and this white one is that one over there. So this green shaded region is the development of data. So if I give initial data here, and I let Einstein equations evolve them, then you generate that much over there. So the boundaries are given by y equals plus minus 1. Okay, so yes. This, no, the green shaded is, so here, okay, if I go back to the previous one, so this is all of the zeta 3, right? So then the green is for all of the zeta 3. And then you can still distinguish, if you wish to kind of just use the inflationary parts, you can go and look at that. Any other question? So I just give, so if I give initial data here, and then evolve with Einstein equations, that's what I get. So this is the part of, so this entire thing is global ADS, and this is the part of global ADS which is connected to it, the zeta part of the boundary. Okay, so far I just described ADS in different ways, describing some of the global issues, but eventually, so what we're interested in discussing quantum field theory in the zeta. So now we have to do something a little bit more than choosing coordinates. Of course, choosing the right coordinates can also be very helpful because it just gives you kind of the right variables. You can always describe a sphere in Cartesian coordinates, but if you already knew spherical coordinates, it's better to use spherical coordinates to describe the physics on the sphere. Okay, so as I said earlier, conformal field theory is value invariant, so it's the same on all conformal invariant spacetimes. So what we want to do is we want to go away from conformal field theory because we want to describe a general quantum field theory. So what I would do is I would deform the conformal field theory by an operator where M is the coupling which has dimensions of mass. So this is a conformal field theory in the zeta, and I deform it with an operator. So since we have a mass parameter, then we break conformal symmetry. So this means this theory here is has no longer relation to vacuum quantum field theory on Minkowski spacetime. There's still a relation between this theory and a theory in Minkowski, but it's more complicated. So if you start from here and do the Wald transformation to go to Minkowski, then this theory becomes this one. So we see that at the position of the future conformal boundary of the zeta 3, when eta is equal to 0, we have a space-like, a singular space-like source function, because we have this 1 over eta here. So if you want to describe physics of the zeta for this type of theory, you may also study Minkowski space with this singular source. Okay, so now, in a sense, now we want to implement that holographically. So we want to. So you could either do the zeta in this theory, or you can go to Minkowski space, but you have to deform it to do a singular deformation. So usually the singular deformations are hard to understand. So still, in a sense, that's probably still a better way as a starting point. So now we want to implement that holographically. So this is the theory we want to study holographically. Okay, but that's to do this, it's a well-known procedure that goes back to the very early days of ADS-CFT. So it goes under the name holographic G-flows. So what we need to do is we need to turn on a scalar field, which is dual to the operator we want to deform. So here we had an operator, we deformed it here with the operator. So we know there is a bulk field due to that operator, and we want this to be a deformation. Oops. So this means that we need to look for solutions which are of the form indicated over here. So it's the zeta 3 invariant. So there is a scale factor, and there is a scalar field that depends on this radial direction. And in order to model the problem we want to model, there are two restrictions on this function p and phi. So as z go to infinity, then we want this metric here to become an ADS in the zeta slice coordinates. And secondly, we want the scalar field to behave like a source. So it should have this behavior. So as long as you have a solution that has these features, this encodes holographically the quantum field theory we're interested in. Okay, now the simplest possible way to do that is to use an action of this form, and this was already discussed in 2017. So you just add a very massive scalar. The mass is such that this is dual to dimension 2 operator, and then one can solve the field equations perturbatively in M. And these are the functions p and phi. So now as you go z to infinity, it's these red terms that survive, and I have precisely the form I want them to have. You can see from here that the leading term is of that form with d equals 3, delta equals 2. And then this should become the form of the zeta ADS in the zeta coordinates, and we've seen this here. So the metric should become of that form, so P of Z should become that function, and okay, this is indeed the case. So now, and we have the solution. So now next is to try to extract the physics out of it. So now we have managed to realize the physics setup we want to realize. We're describing a massive quantum field theory in the zeta. Now let's start understanding global issues. Now one can find coordinates where the solution takes the form given over here, where the omega and f are given perturbatively like so. And now you can see that this is, again, the metric is conformal to ADS. This means we can represent it. You can use the same Penrose diagram I had earlier. So this is the case of ADS, just ADS. And this is what happened when I turn on the scalar. So this singularity here. So here we did, from the perspective of Minkowski space, we did a singular deformation. And then this singular deformation, so this point here, before you turn on the scalar, propagates as a null line. After we do the perturbation, this null singularity is now split into space-like and time-like ones. So again, the null y equals 1 singularity splits into space-like and time-like, which you can compute perturbatively. And we also study what happens at finite m, and numerically, and this is the answer. So this is the position. So this describes that curve over here for finite m. Well, once you turn on the perturbation, you can see what happens to the position of the singularity, and this is now the solution. So the y=1 line is now deformed in this fashion with plus and minus. Yes, yeah. So it's actually go back to you can see it's the development here stops when we first meet the singularity. So it's always the minus one. Well, I think you should think of it that this is you excise the rest of this diagram, and your space-time it kind of finishes there. So here it starts like 1 over y, and this is the propagation of that point to the bulk. Well, I mean the asymptotics. And the space-time cannot be extended past this point. So from our perspective, this is the end. So if you said nothing can go to y=1. I mean that's now your space-time. The space-time is this new green region. Let me see, did we? Well, I mean, you can start from the explicit metric and work out the curvature. I don't remember exactly what happens. Yeah, so what we're claiming is that time evolution from here would never get you past that point. Yes, yeah. I mean, you have to have some singular object in the bulk. Maybe you have some brain there. It can be another site. Yes.
And then you put the boundary of one such copy. But the Cauchy evolution takes you away from the bulk region of the sitter when you take this boundary. Right? Because you have the
But now I put. So initially I have. So here this is an artificial kind of separation. I said if I put data here, that is how it's going to evolve. Now I have also a scalar field, and that's what makes the difference. So now it's a coupled system. And here, I don't have anything, I cannot go beyond that point because the sitter, minus infinity in the sitter is here, plus infinity is over there. There's nothing beyond that point.
So, if you have confused, so I understand that the boundary of the, initially when you have the two has this is a boundary of one, right? But it's not really a boundary because the evolution takes you away from the bulk because there is this green shaded region above the digital bulk, right?
No, but that you should think of this again. It's this boundary is here, and then it's this. There's infinite distance between here and there, so it's the infinite past of the sitter, the infinite future of the sitter. There's nothing beyond infinite future of the sitter. It doesn't make sense to say you want through there. And then once you have that geometry in the boundary, then you ask, what is the evolution in the bulk? And now, in the case of just ADS, that would be the region which is covered. Now, in the case where we also have the scalar field, it's a back-reacted system, and then that changes into this one. But once you put the scalar field, because that really diverges at y=0, I mean, here was a choice. I just say I chose that data. But here, the scalar field diverges here. you cannot go beyond that. Okay, so now we have the solution. Let's try to extract the physics. And to extract the physics, so now we have the bulk solution, then we use holography. So we can extract the correlators using holographic normalization. So first, one-point functions. The one-point functions, their form is dictated by de Sitter invariants and Ward identities. So the energy momentum tensor, it has to be proportional to the de Sitter metric at the level of one-point function. Then this is an object which is dimension 2. And then that's why we have the Hubble function square. And then in general, these are multiplied by general functions of the ratio of dimensional ratios of mass with the Hubble function. And the fact that the same function appears here and there is due to Ward identities. Now for small m over h, you can use the solution to extract the form, and it's given by this expression. So since this is a small m over h, and we know there is a leading order effect, so this had to go like linear, like m over h. And then we know that the back reaction with the metric is quadratic in m, because it's the energy momentum tensor of the scalar field is quadratic, and that's why here you have this factor of m over h over there. Now, when we go to the opposite regime, where the mass is much larger than the Hubble function, then this function, again, on general grounds, had to be of that form. And the reason is that in this region, the scale that dictates the physics is the mass. So this means that in this formula here, h should disappear, and the dimension should be saturated by the mass. So it has to be like m squared over h squared with some undetermined coefficient. And that coefficient we computed numerically. Okay, so this behavior here is the small m perturbation theory. One can also compute the behavior with the leading large m behavior, and then the dots are with numerics. And then the value comes from the numerics, the slope. Should be possible, well, it may be possible to derive it exactly, but that's 10 minutes, okay. So we're gonna accelerate, appropriate for the sitter. Okay, so next, so now we understood one-point functions, next is two-point functions. And to compute those, one can again use the technology developed in the context of normalization group floss. So to derive two-point functions, we need to perturb the metric and the scalar field. Then to utilize the symmetries, we decompose the perturbations in the de Sitter invariant way, and that's the way to do it. And the system has basically 2 degrees of freedom. There is a scalar mode, and there is a transverse traceless mode. Now we also know the problem has de Sitter asymmetries. So this means we can organize it in such a way to make this manifest. So if one uses inflationary patch, then 2 of the coordinates, this translation invariance, and we can use a kind of momentum in these directions. And then we can use the fact that you can expand in eigenfunctions of the de Sitter 3 the Labertian. So then the general solution can always be written in a form given over here, where this part here takes care of the flat directions. This is the de Sitter, that kind of the time direction. The lambda is the eigenvalue over here, and then what is left is to determine this function of the radial direction. Okay, so I kind of For the tensors, again, this is the decomposition, and then that's the equation that one needs to solve for one scalar function, because we now factor out all the tensor indices. And then you solve this, and then from there, using standard methods, you extract the answer. And this answer is given in this expression over here, where nu here is the index of the Bessel. You can see, so here we describe this. So I have k are the momenta, and u is the index of the Bessel function. So the answer has some polynomial and has some poles, one nu equal to 2, which are high and high order. Now it turns out actually that one can understand the structure here in a bit more detail. So in the background, I could yes. It's not entirely clear whether it's the Bunch-Davis. I would think it is the Bunch-Davis, because of course we haven't done perturbative quantization in the sitter. We're just using holography. So here the mode functions are chosen by regularity in the interior. So the way that so in the eta direction, the form of the equation, you land either into J's or Y's rather than Hangels. So usually if you do perturbative quantization in the sitter, you will get Hangels. But here you get the Y's and the J's. And we chose the J because the Y blows up in the interior. Okay, there is, so in this geometries support normalizable modes. So these normalizable modes start off by the normalizable modes in ADS, the ones which are de Sitter invariant. And then there are corrections because we deform the theory. And one can rewrite the answer such that it has a polynomial piece and only has a first order pulse in the position of the normalizable modes. So this is a sort of spectral decomposition. And then the same story is true also for scalars. And again, one can write it. Let's skip a slide. Yeah, for the scalars, the analysis is slightly more complicated because one has to consider gauge invariant variables first. That's a bit of a technicality. I can describe it later if you want. But then once you get the answer, the two-point function is given in this format, where again you can do the same resummation as before. To write it, there is now a single nu, and then there are poles. And then the poles are always the poles at the normalizable of the normalizable modes with specific residues which are all computable. Now, if we set m square equal to 0, this means no deformation. We just have a CFT. So the answers should go back to the answers of a standard CFT. And this is indeed the case with a kind of a non-trivial, using some non-trivial identities that goes back to almost 200 years ago. So you can expand plane waves into Bessels. And then using this, one can show that this expression here becomes the standard expression either in position or momentum space. But this expression here, the ones that we got with the Bessel basis, is extremely simple. So this is the two-point function for general operators. So if I normalize them with the index of the Bessel, then the entire correlator all conformal scalar two-point functions just become that of free harmonic oscillators. So this looks like a free field realization of general CFTs. So I mean, that should have a better understanding. Okay, so how many minutes? Minus 3. Okay. Okay, so now let me very quickly go through a toy model. So what we did is we deformed the theory, the conformal field theory, by an operator of dimension 2. So if we're in 3 dimensions, then an operator of dimension 2 is just the mass term for a fermion. If you have 3 fermions, the mass term has dimension 3. So it turns out that theory has many similarities with the theory we found holographically. Then you can use conformal perturbation theory by using the mass as a small parameter. So if you're at a fixed point, vacuum values are 0, the two-point functions take a standard form, the three-point function of a free fermion turns out to be 0, and this is non-zero, but somewhat complicated. And you can use that to then compute the expectation value in the deformed theory by using conformal perturbation theory, and one gets precisely the answer that we got holographically. Now here, there is, in a sense, that's where some of the issues with the infrared singularities come back. So if you would do the same computation in lambda to the 4 theory, as was done first by Bunch and Davis in 78, and if you compute the expectation value of phi square, then that goes like h square over m square. So that diverges as m go to 0. This is part of the story with the infrared divergences I was summarizing in the beginning. So in this case, you do not get this. One gets that the mass appears in the numerator. And then you can go to two-point functions. Again, you can expand in M. Since the three-point function is 0, this goes away. And so one gets that the two-point function is that of the CFT up to corrections of order m square. That's precisely also what we found. In principle, these are computable, but we haven't computed them. So up to the order that we checked, this toy model agrees with the holographic predictions. Okay. So let me now quickly summarize. So what I did today is I show you a study for strongly coupled quantum field theory in a de Sitter 3 background. So in this case, we found no signs of infrared instabilities. So this may suggest that the issues are really with perturbation theory rather than with the theory itself. At the same time, this is perhaps not surprising because the quantum field theory itself was a deformation of a CFT. So when you set the mass to 0, you get a well-defined theory. Where in the case of the theory that people studied in the past, like 5 to the 4 theory with a mass term, then the theory is not a well-defined CFT when the mass is equal to 0. You need to have an improvement term. We also found that the two-point functions are expressed in a spectral representation as a sum of simple poles. That probably has a deeper understanding. And these poles all correspond to normalizable modes. Okay, so what's in the future? Well, first, I'd like to extend this to de Sitter 4. I mean, I started with the motivation that we live in a universe with positive cosmological constants, so the relevant dimension is 4. And also we want to extend this to FRW. We use a toy model. There was no potential, but one could introduce a general potential. I think most of these generalizations are doable. The de Sitter 4 is in progress. There are some differences and some technicalities. But once you have this, I would like to make the connection with cosmological observables, because now we would use a strongly coupled quantum de Sitter quantum field theory and see how that compares with kind of CMB observables. And finally, I think it would be interesting to further explore this novel Bessel basis for safety correlators that kind of seem to almost trivialize them, kind of make them like free harmonic oscillators. Okay, thank you. So in the past, people did not have the scalar field, and therefore there's no difference between that part or any other one. One will have to include the other parts as well. So the fact that we have the scalar field that diverges at the position of at equal to 0, that's what makes the difference. I mean, infrared issues definitely depend on the vacuum. Yes, that's. I think for me, in a sense, the reason I don't find surprising everything was stable was because when I set the mass to 0, I get a CFT, which is well defined at all scales, has no problems in the infrared. Where in the past, the models that people consider, they did not have an a priori well-defined limit in the infrared. They just started from the simplest, what looked like the simplest theory, but which in retrospect is a more complicated theory because has. I did, yes, yeah, it is. Maybe it's an alternate Bunch Davis because I don't understand directly from the field theory. In a sense, it's natural boundary conditions from holography, but it may not be as natural from the perspective of the quantum field theory. Yeah, I don't see why it's not unitary. Yeah, it looks like unitary.
I have a quick question. So, do you know whether this construction is stable because of this space-like?
I mean, from the perspective of the kind of the sitter, yeah, I don't see any issues. There are no instabilities. No, I mean, I mean, we study completely the linear perturbations. Yeah, there's no, yes, there's nothing that grows. Yes. I mean, once we, in a sense, impose natural boundary in initial conditions, then the system evolves in a well-defined way. We don't see any sickness of any type.
Okay. So then we should move to the next talk.
Okay, I just wanted to thank the organizers from IIT Madras and Southampton for this conference. I will give a talk which is based on this work with very good graduate student Elliot Gesto and Matilde Marcoli, and it's on trying to think about holography on fractal spaces. Is there a pointer here? No. It's okay, I'll just do the same thing as you. Yeah. Okay. Okay, so the main question that I want to ask, I hope this is white is visible, is what kind of spaces admit a holographic correspondence? And this is an important question, and we already know that asymptotically ADS spaces can allow dual theories, but we are also interested these days in flat space holography or de Sitter holography. So this is an important question, but I want to attempt to address this question in the discrete setting. So in the case of discrete holography. So what I want to do in this talk is propose a large class of discrete spaces, new examples where we can have holography and where the dimension of the boundary is not necessarily integral, and it can be fractal as well. Okay, so let me first just describe some very well-known attempts at discrete holography from some time ago. The first easiest thing to do, well, there are many attempts at discrete holography. The one which I will focus on in this talk is tessellations of hyperbolic disk. So I'm thinking of, let's say, ADS space. You're looking at a time slice, and that's a hyperbolic disk. In this case, hyperbolic disk. In general, it can be some hyperbolic space. And one thing we can do is we can look at holographic tensor networks. So these tensor networks represent are some kind of toy models of holography which capture some nice features of holography, like entanglement, entropy of boundary, and emergence of space-time in terms of tensor networks. There are other things you can do, and Rene will give a talk on this, so I will not go into this. But you can have scalar dynamics, or you could try to describe some kind of a CFT which lives on the boundary of these tessellations of hyperbolic disk. Another thing which is more recent, which I did with my collaborators, was p-adic version of holography. So I will describe that. I will mention a few things about these two attempts. There are other attempts also. I don't want to go into them because they are not directly relevant for my talk today. Okay, so the first one I mentioned was tessellations of hyperbolic space. So here there's a hyperbolic disk, and it has been tessellated using pentagons, right-angled pentagons. So now this has become a discrete system, and one could imagine doing dynamics where we say that, okay, there is some field which lives on each of the faces of the tessellation. So it's a discrete system in that sense. And what people did was this work by, it's called the Happy Tensor Network. They set up a tensor network on the dual graph of this tessellation. So at each face you put a tensor, and you compose all the tensors together, and you basically end up with a mapping between the tensor is a mapping between the red legs in the bulk and the white legs on the boundary. So this is a way of describing some kind of an isometric embedding, isometry between the bulk legs and the boundary legs. So in more detail, what is an isometry? In general, it's just a linear map which preserves the inner product, and generally it's from some Hilbert space to another Hilbert space. And the tensor network that these Happy tensor network people constructed initially was based on a special kind of isometry, which are called perfect tensors. So they are even index tensors, and here the index would correspond to the number of legs in the Hilbert space A and number of legs in Hilbert space B, for example, but locally. So here there is 1, 2, 3, 4, 5 and 6 legs. So each of these blue plaquettes is a tensor, and a perfect tensor is an isometry which is actually a unitary transformation for any equal bipartition of its indices. So one can construct a mapping, an isometry from the bulk Hilbert space, which will be what is called a code subspace, because it represents the low energy dynamics of the boundary CFT. So we are mapping the low energy dynamics of the CFT, the code subspace, to the full CFT Hilbert space, which is called the physical Hilbert space, using a tensor network built out of perfect tensors. So dangling legs in the bulk get mapped to dangling legs on the boundary. No, any 3. If this is a 6 index tensor, then any 3 will be a unitary transformation to the other 3. Yeah, so for perfectness condition, red one is not special. Yes, yes, right. Okay, so I don't want to go into the details of this paper, but I just wanted to say that what they found was that if we model our holographic system like this, so there is some, the red legs are free legs, which represent, say, your code subspace, and your white legs are the free legs on the boundary. Then this represents some kind of a reconstruction of the bulk, when you can say that you input some operator in this red leg and you input identity everywhere else, and you're trying to reconstruct this operator on the boundary. So your tensor network is providing a mapping of how to go from the bulk input to the from the bulk operator to a boundary representation. So this is one example of a reconstruction, bulk reconstruction. But what these people found in the happy tensor network construction was that it has a lot of desirable properties of holography. So for example, it has a version of Ryu-Takenagi formula. So if I were to kind of think about Ryu-Takenagi as in the entanglement of a set of boundary legs with the complement set of free boundary legs, then in this case the answer will depend on the there will be a minimal geodesic which will cut across the tensor. The area of the geodesic corresponds to how many cuts you have made in the tensor, and the Ryu-Takenagi formula will tell you that the entanglement of the boundary region that you have chosen with its complement is equal to the area of the minimal surface plus the entanglement of the bulk legs which are inside this entanglement wedge. So there is a Ryu-Takenagi formula. There is also entanglement wedge reconstruction, which is kind of like subregion duality, where we say that if you choose some region on the boundary, then there is an entanglement wedge of that region, and any bulk operator inside the entanglement wedge can be reconstructed by operators on that particular boundary. While you can do the same for the complement. The operators in the complement of the entanglement wedge can be reconstructed in the complementary boundary. So that's related to complementary recovery also, and it also has quantum error correcting properties because of the subregion duality. So for example, if I give you a region and then there is an entanglement wedge corresponding to that region, then all operators in the bulk inside that entanglement wedge can be reconstructed on the boundary Hilbert space. But if I delete anything on the complement of the boundary region, it does not affect my knowledge of the bulk operators. So I can still construct the bulk operators here. I only need to know what is happening here in this boundary region. I don't care if something is deleted elsewhere. So there is a natural quantum error correction which is encoded in this tensor network. Okay, the drawback of this tensor network was that it only worked for certain boundary regions. It did not work for any arbitrary choice of boundary regions. So for example, if I picked some 5 white legs as my boundary region, it might not work. All these formulas might have some error, small error, or maybe large errors. So it only worked for certain regions. And the regions it worked for, the happy people came up with an algorithm for constructing the Ryu-Takenagi surface. So that's called the greedy algorithm, where you say that you start from a choice of your favorite choice of boundary region, and then there is an algorithm which step by step constructs a minimal geodesic. But this greedy algorithm fails to construct the minimal geodesic unless the chosen region is of a certain kind. So there was this problem that this tensor network construction only worked for specific choices. And these specific choices, this is not very surprising. The reason is that in continuum ADS CFT, we expect that the Ryutakyanagi formula, entanglement wedge reconstruction, complementary recovery, all of this will work for arbitrary regions, but not in this discrete setting because we have broken the conformal group due to the tessellation. So the conformal group has been broken into a discrete subgroup. So we don't have the full conformal symmetry, so we cannot have, we cannot expect things to work for all boundary regions. So the reason for that, certain choices will, as I will say a little more later, will be related to the fact that the isometry group of the bulk or the conformal group of the boundary has been broken into a discrete subgroup. Okay, so those were some of my comments on happy tensor network and related tessellations of related tensor networks on hyperbolic tessellations. Yeah. Yes, I will. Yes, yeah, yeah. Okay, so another kind of discretization, and actually it's kind of related in some sense to the happy tensor network discretization, is here we have what is called a 5,4 tessellation of hyperbolic space, by which I mean that it's tessellated by pentagons and 4 pentagons meet at each vertex. Now if you bump up the number 5 to 6, 7, 8, so on, once you go to infinity comma 4, you get a tree representation, a tree tessellation of ADS, this hyperbolic disk. So this is what happens in p-adic holography. We kind of, instead of looking at the hyperbolic disk, we look at a tree, which you can think of as an extreme version of extreme limit of the tessellations I was discussing earlier. Now the interesting thing is that when the number 4 here is such that it's some prime number plus 1, then this kind of tessellation has very interesting algebraic properties, and this leads to p-adic holography. So I don't want to discuss that, but I wanted to mention that just like in the case of the happy tensor network, you can have Ryutakyanagi formula and complementary recovery in the p-adic case, but now the entanglement of the boundary is logarithmic in the p-adic size of the boundary region rather than the let's say L2 size of the boundary region in real space. Okay, so that's one nice thing. The other nice thing, so I hope the reason I'm spending some time here is I just want to motivate why discrete holography is useful, because it's kind of like a toy model where we can try to understand some aspects of holography, like quantum error correction, without having to deal with lots of conceptual issues. Another reason why p-adic holography was useful was that, and it's not related to tensor networks, is that the simplicity of the tree made calculations in the bulk space very easy. So all ADS integrals become geometric sums and just come down to counting points on the tree. So you can have propagator identities like 3 bulk-to-bulk propagators integrated over a common bulk point, and you can write down these explicit answers, which you can. Once we know these answers, we were able to generalize this to continuum ADS space. So this was a practical application of p-adic ADS CFT, that we had bulk propagator identities for continuum ADS starting from the p-adic answer. The answer is just a small generalization of this. Well, the periodic answer does not involve any descendant contributions or higher trace contributions, where you can kind of add them in the continuum case. And then you can use such propagator identities to work out, for example, higher point conformal blocks, or you can use these identities to simplify higher loop ADS diagrams. Several classes of higher loop ADS diagrams, you can decompose them into tree level ADS diagrams using identities like this. Okay, so these two examples are two examples of discrete ADS CFT. There are many more that people work on. The reason I mentioned these two are that both of these can be generalized by a structure. So, yeah. No, there's no new identities. It's just that some calculations are easier to do on the tree. But the answer is very similar to the answer which you will get in continuum space also. So knowing the tree answer, you can then work out the continuum answer. So it's just as a helpful starting point to work out more complicated calculations. Yeah, so the loops are kind of there. You can still have loops. I can say a little bit more about that, but it's not related to the talk, so I prefer to say this afterwards. Yeah, but that's a good point. How do you think about loops on trees? And you can think about loops, but there is some subtlety at the level of sub-ADS scale. The tree does not involve any sub-ADS length scale, so then you miss out some things at sub-ADS length scales. But this is, by the way, this is not a loop. This is just a product of three propagators. So there's only one integration, which is the green dot on the left. So it's like a star triangle identity, but in ADS space. Okay, so one of the questions is, in both these cases, in the case of periodic holography and in the case of the happy tensor network, the boundary of the tessellation in the happy tensor network is homeomorphic to a circle, more generally a sphere. And it turns out the boundary in this case is homeomorphic to the periodic circle. So it's still a circle. Yeah, so it's a limit of the tessellation, but once you take this limit, it actually picks up a full, this whole thing becomes isometric under the full conformal group, but now it becomes the periodic conformal group. So in that sense, you have not lost any symmetry. So when you do discretization tessellations, you lose symmetries. Yeah, so you can, yeah, right. So in this paper, we also looked at black hole geometries, and the nice thing is that BTZ black hole we think of as a quotient space of ADS, and since everything is very algebraic here, the tensor network is algebraic in terms of a periodic conformal group, you can quotient it and you can get a black hole answer, and then that black hole tensor network is different from the tensor networks that, for example, Happy discussed. What isometric? Non-isometric. Yeah, so here, no, so black hole interiors are not that, periodic holography does not help with black hole interiors, because for it, the black hole, basically the interior of the black hole will be empty here in this setting. Once you take a quotient, there will be nothing inside. Yeah. Yeah, so I mean, the limit set is a Cantor set here, but it has an interpretation in terms of, so if you were not thinking about p-adic numbers, then you would just say that it's some Cantor set. But in terms of p-adic numbers, it's the projective line over p-adic numbers, which is like, you know, the projective line over R, which is your S1. So it just happens that in the case where you take the infinite tessellation limit, you get the p-adics. So it could be a happy accident, and then we can exploit it. Okay, so we can ask, can we construct holographic tensor networks where the boundary is not homeomorphic to a sphere or circle? And we can also ask, what are the geometric structures which underlie these tensor networks that we discussed? Like, those seemed very different constructions, but they have similar properties of holography. Is there some mathematical geometric structures underlying these tensor network constructions? And one problem I already discussed was classifying the boundary regions where Ryu-Takenagi works, complementary recovery works, entanglement wedge reconstruction works. Because it does not work in all boundary regions because the conformal group has been broken. And how do we determine if we have constructed a tensor network that it has good quantum error correcting properties or good holographic properties? So a quick answer which I will discuss to these questions is that yes, we will find something called hyperbolic buildings, which of which the previous two things that we discussed are special cases. So there is a unifying structure, excuse me, which subsumes the two cases earlier. It subsumes many tensor network constructions which arise from tessellations. The geometric structures we will see come from well-studied mathematical subject of Gromov hyperbolicity, which we will discuss, and classification of boundary regions that are good boundary regions will boil down to studying the isometry group of these hyperbolic spaces. And I will in the end provide a list of properties that your holographic these buildings must have so that they are holographic. So what are these buildings which generalize the tessellations? And this comes to the higher dimensions that you mentioned. So in real life, we look at buildings as, here are examples of two buildings. And now I have shown two rooms, which we call chambers in the building. And a collection of these chambers will become an apartment. So here there is an apartment, it contains a bunch of chambers, here's another apartment, and a bunch of apartments together give a building. So that's the general idea that this is the origin of the terminology, but it's a mathematical terminology. So these are not the buildings that we will discuss. These buildings are probably not holographic, but we will discuss some which are. So what are the buildings that mathematicians like? They look more like this, this figure. So I will explain that figure in a bit, but what is a building? I'm trying not to be very mathematical, but still I have to use some words here. So a building is a polyhedral complex whose subcomplexes are apartments. So it's what we said earlier, buildings are made up of apartments. Now these apartments will be tessellations of either the hyperbolic space, the Euclidean space, or spherical n-sphere. So apartments are made up of chambers like before, and they are tessellations of one of these three. So you have to pick which building you want to consider. Do you want a hyperbolic building? Do you want a Euclidean building? Do you want a spherical building? So you tessellate your space by chambers, and this tessellation will give you an apartment. So far it does not contradict what I showed in the previous picture. I mean, I just would have to say that now this is a tessellation of Euclidean space and it is infinite in extent. But this is the point where now we can no longer use the buildings in everyday life. You pick any two chambers, they must belong to an apartment. So any two chambers must belong to an apartment. Here, this chamber here with this chamber here, they cannot belong to the same apartment. They are in different apartments. But in mathematical buildings, any two chambers will always be in a common apartment. and there will be many apartments in which they will lie together. And finally, between any two apartments, there will always be an isometry. You can isometrically transform from one apartment to the other while preserving the intersection of the apartments. So here's an example of a Euclidean building, by which I mean that the chambers here are these triangles. The apartments are the tessellation of E2 Euclidean plane with triangles. So I don't have a picture of that, but you just imagine a triangles tessellating Euclidean space, E2. So that's one apartment, but this building is made up of all the apartments glued up together like this. So there's a lot of branching. So that's the main point, that in mathematical buildings that we discussed, there will be branching because of this fact that any two chambers must be in an apartment. So these two chambers belong to an apartment, these two also belong to an apartment. They all belong to different slices of Euclidean tessellations. Today we will not discuss Euclidean buildings. Yeah. No, they intersect with each other. Yeah, all apartments intersect because any two chambers have to be in an apartment. So they intersect. In fact, I mean, this is only a part of a building, not the full building. The full building you cannot draw even in 3 space. There will be intersections between chambers, which chambers cannot intersect. But when you try to just show it visually in 3 space, you won't be able to. Yeah, I will come to that in a second. Yes. Okay, so let's talk about the buildings that are important for holography, and the Bourdon buildings are the simplest ones. These are hyperbolic buildings, so their apartments are tessellations of hyperbolic plane actually. So here n equals 2. So I'm setting n equals 2. I'm looking at hyperbolic plane or hyperbolic disk actually, and P will be greater than or equal to 5, Q greater than or equal to 3. That's not very important for us. The chambers will be right angled regular p-gons in H2. So if you think about the happy picture that I had, that it had pentagons. So those were chambers, and a collection of these chambers gave the full disk tessellation. So that would be an apartment. So chambers are glued at their edges and vertices, and 2 chambers share at most 1 edge or 1 vertex, and we can make apartments out of these which tessellate H2. And at each edge, exactly Q chambers are attached. So think about Q equals 2. If Q equals 2, then if you look at this, it's kind of, yeah, here, you have pentagons. These are chambers. 2 chambers are incident on each edge, and they tessellate the hyperbolic disk. So this is what I would call an apartment. This is an apartment. Or you can say this is a building which has only one apartment. So this is a simple example of a hyperbolic building with only one apartment. So there is no branching. But now if I said Q equals 3, so now at each edge there has to be 3 pentagons. Then suddenly we will have branching of the kind I showed here. This kind of horrific looking branching, because no, yes. So it's different. It's not slicing of ADS because there is no one time direction in which the apartments are going. The apartments are going in all fractal, kind of like a fractal directions. So they're actually growing in a Q-valent tree for Q equals 3 or higher. So Bourdon buildings is actually just a unique 2 complex which satisfies these properties. And for Q equals 2, we get back the tessellations. Okay. Instead of right angled triangles, if right angled p-gons, if you were allowing p-gons which had dihedral angles, which were integer submultiples of pi, not necessarily right angled, then you can get other tessellations for Q equals 2. So you can basically reproduce all hyperbolic tessellations by choosing the right angles here. But the Bourdieu buildings are the ones with right-angled pegons. Okay. So here's the picture again. This is an apartment, and this you can call a building 5, 2. Q equals 2. When Q becomes 3, I won't be able to show you the building, but I can at least show you what happens locally at one particular vertex X. So at one vertex X, now instead of 4 incident chambers, it turns out we have 8 chambers which are incident. And that's just a consequence of the fact that Q equals 3. When Q equals 3, if you look at this picture, at any edge, you will see there are 3 faces which are incident. It takes some staring at, maybe it's not visible, but this is the kind of branching which you have to now glue together at each vertex, and that gives you the building. I don't want to discuss the link, the definition of link. It's an important object which is very useful in proving various holographic properties, but I won't use it directly. So let me not discuss that. But I only want to say that link is a local property of a vertex, and for these Bourdieu buildings, the link is always a bipartite graph. So the main take-home message from this slide is that there is branching at Q equals 3, and at Q equals 2, we get a single apartment. So here there will be infinitely many apartments which are intersecting with each other. Okay, so these apartments are associated with a Coxeter system. So now maybe this is a slightly more technical slide. A Coxeter system is a pair of Coxeter group with a generating set S. The generating set S corresponds to reflections about the faces of the pentagon in this case. So if I label the central pentagon as identity, then reflection about S1 gives me this, reflection about S4 gives this, and there are 5 different reflections because there are 5 sides. But I can keep doing reflections. Once I get here, then I can reflect, and then I can reflect, and I can keep reflecting. So basically I can approach any chamber using the reflections. So the Coxeter system basically gives us a way of isometrically going from one chamber to the other inside the same apartment. Yeah, so this is an example of a Fuchsian group. But this is more general. Fuchsian group would be some version of this, I think. But the isometry group of the full building is not the group. So this group, W, is the discrete subgroup of the isometries of hyperbolic space. This is the one where, in happy tessellation we said that the conformal symmetry group is broken into W. But the building now for Q greater than 2 has a bigger isometry group, because now we also have to allow for isometries from chambers which are branching out. Okay, if Q equals 2, then this group is the same as the group I showed earlier. But for Q greater than 2, the isometry group becomes this gamma p comma Q. Now the nice thing about these buildings is that these buildings have a mathematical notion of what is happening at the infinity. That's called the Gromov boundary. And for Q greater than 3, the boundary is a Menger sponge. So it's no longer a sphere, as I was saying, that we want a tensor network which is whose boundary is not a sphere. Now it's a fractal here. And the Hausdorff dimension of the boundary is related to the growth rate of the isometry group and the growth rate of the Coxeter group from the previous slide. So if both the groups are the same, if Q equals 2, then the isometry group is the same as the Coxeter group, and the Hausdorff dimension of the boundary is 1. The Coxeter group only takes you in a single apartment. It isometrically maps chambers to other chambers. It does not go outside the apartment. The isometry group is for the entire building, which includes all the apartments. So when there is only one apartment, then the isometry group is the same as the Coxeter group, and then the Hausdorff dimension is 1, which is the case of the p-adic and happy tessellations I discussed. But for Q greater than 3, now your Hausdorff dimension becomes fractal. And then we see that the now the Ryu-Takenagi formula will no longer be logarithmic. Now it will be power law, and the power law will be dictated by the Hausdorff dimension. So just to show what a Menger sponge looks like, the boundary is homeomorphic to a Menger sponge. It's not exactly the Menger sponge. You can, do a diffeomorphism to the Menger sponge. So what is the Bourgeois tensor network? It's the same as the happy tensor network. We insert a perfect tensor inside each chamber, and we contract legs of the tensor wherever there is an edge which is shared. And now instead of one bulk dangling leg, we include q minus 1. Q equals 2, it gives back 1. But you can also change q minus 1 to other things, but q minus 1 is the simplest thing to do. And then we always have to have some cutoff, and we cut off the tensor at some distance. So this is the tensor network. So this is roughly the answer to the first question, that there are these hyperbolic buildings which give us the tensor networks which kind of are higher dimensional. But by the way, n was still 2 for Bourgeois tensor, so it's still in the sense, the apartments are tessellations of hyperbolic plane. Yes. Once you have a cutoff, then you can kind of have a notion of layering, that this is the first layer, then there's a second layer. Even with branching, you can have that notion. So you can have a central tile. Yeah, thanks. Okay, so now let me quickly go through the other points. So I mentioned about boundary of these Bourgeois buildings, and that comes from the theory of Gromov hyperbolicity. And it depends crucially on an important object called the Gromov product. So if you have a metric space X with a distance function D, then Gromov product is defined as this combination. So roughly, if you had a tree with X, Y, and Z on the 3 edges of a tree, then Y, Z with respect to X basically tells you that you first count the distance between X and Y, distance between X and Z, and then you subtract the distance between Y and Z. So you end up with kind of like what is the lowest common ancestor between X and the lowest common, the distance between lowest common ancestor of Y and Z and X. So it's a nice metric, and using this you can actually define a notion of Gromov hyperbolicity, which is actually a generalization of notion of curvature of manifolds. So now you can define curvature in graphs, etc. So this is very useful in geometric group theory. And if your space satisfies the criteria, then you say that X is Gromov hyperbolic. In this space, you can also define geodesics in X, and you can have an equivalence relation that in hyperbolic spaces, Gromov hyperbolic spaces, if two geodesics do not separate from each other, they remain bounded distance from each other, then they are identified by this equivalence relation. And with this identification, the equivalence classes of this identification give the Gromov boundary. So all this to say, these are very abstract concepts, but the point is that these are very well-known constructions. So once you have Gromov product, Gromov hyperbolicity, you also have a Gromov boundary. So you have a bulk space, you get a boundary space. And this Gromov product can be used to induce a natural boundary metric. So you also get how to calculate distances on the boundary. So these are all things which we kind of desire in holography. How to calculate distances in the bulk, in the boundary, what is the boundary, all of this is very rigorously known in the Gromov hyperbolicity language. Okay. So using this Gromov hyperbolicity, we can now address the remaining questions. So one of the things I discussed was entanglement wedges. So in the case of happy tensor network, the entanglement wedges were the regions you get, the region enclosed between a geodesic and the boundary. So you have a geodesic in hyperbolic plane, hyperbolic disks, these are just hemispheres. semicircles, and then you have some bulk region which is enclosed between the semicircle and the boundary, and that geodesic cuts the bulk space into two connected components. One is the entanglement wedge, one is the complementary entanglement wedge. Now when Q is greater than 2, then we have fractals coming once again, which is not surprising. So I guess in the interest of time, I will not go into this construction, but again, there is a very well-defined notion of walls and tree walls, which actually turn out to be what we need for Ryu-Takenagi surfaces. So for Q equals 2, these tree walls become the Ryu-Takenagi surfaces. For Q greater than 2, they are still Ryu-Takenagi surfaces, but now they are not surfaces, they are actually Q-valent homogeneous trees. A 2-valent homogeneous tree will just be a line, but higher Q, they become these trees. So the Ryu-Takenagi surface has a fractal nature. And it cuts the entanglement wedge not into two components, but Q-connected components now. So that's one kind of entanglement wedge. The other kind of entanglement wedge, I guess we don't need to worry about this distinction, but you can have two tree walls to define an entanglement wedge. And the point is that the nice thing about these boudoir buildings is that the apartments are happy tensor networks. So happy tessellations. So a lot of proof about Ryu-Takenagi, complementary recovery, entanglement wedge reconstruction, subregion duality boils down to proving those things for happy tensor networks, which have already been proven. Once we have the correct ingredients, proving that these boudoir buildings are holographic is not very difficult at all. All the work, hard work, is already done in the happy tensor network case. So since I did not discuss tree walls and entanglement wedges, I'll just skip this. Okay, so this is what I was saying, that if your boundary has dimension d equals 1, the time slice of your ADS space, for example, has dimension d equals 1, then we expect that the entanglement entropy will scale as logarithm in the size of the region, or else it will scale as a power law for d not equal to 1. And the previously known tensor network constructions always led to logarithmic answers because d was always 1. But now we have a building where d is fractal, and what we see is in fact the Ryu-Takenagi formula in this case is now a power law where d is that Hausdorff dimension. Okay. Yes. 3 minutes, okay. So Ryu-Takenagi surfaces are fractal and they see the fractal nature of the boundary. Okay, so I guess in this slide I was going to explain a broader class of buildings which also are holographic. So I gave you one specific example, which is these boudoir buildings for some values for P and Q greater than 5 and 3. But there is actually an infinite class of hyperbolic buildings which satisfy holographic properties. So these were some conditions. Let me not go into them. But I wanted to mention something about n. So far n was 2 for us, but we can also construct these buildings for higher n. The only problem is that there are some restrictions on n. So right-angled tessellations are only possible when n is less than or equal to 4. So if you relax the right-angled condition, you can have tessellations up to n equals 29 and still recover all the holographic properties that we discussed. But if you want to go all the way to all possible n, then we have to even relax the condition that the apartments are a regular tessellation of hyperbolic space. If we let the apartments be some kind of patched together copies of hyperbolic spaces, then there is a very concrete construction of buildings called the Davis-Mousson construction. And again, we can check that it satisfies all the holographic properties that we like. Okay, so let me just summarize that there are these hyperbolic buildings which generalize tensor network constructions. So earlier tensor network constructions can be thought of as a single apartment. Now we have like crazily branching set of apartments. They still are holographic. They are sensitive to the fractal dimension of the boundary. And this fractal dimension arises, for example, in the Bourdon case due to the non-trivial branching for q greater than 2. So there are a large class of such examples where holography should be possible. So this is my final slide. Some things to consider are we have relied heavily on properties of perfect tensors, which is because the happy construction relied heavily on perfect tensors. But we can attempt to go beyond them and try other tensors in the tensor network. We have not discussed disconnected boundary regions. All our regions were connected boundary regions for calculating entanglement, let's say Ryuta-Kenagi, etc. Okay, this third point is kind of, I skipped over it. So let me just say that there is some question about which fractal dimension is the Ryuta-Kenagi surface sensitive to. Is it the scaling dimension, the Hausdorff dimension, the box counting dimension, which one? It looks like it is the scaling dimension, but in all the examples where we can concretely check Hausdorff, scaling dimension equals the Hausdorff dimension. But it's not always the case, and this question is actually deeply tied to some open problems in geometric group theory. When can we actually calculate the Hausdorff dimension, and when can it equals the scaling dimension? Okay, we can go to black hole geometries. The other interesting thing is that we have been discussing the bulk story only, but what about this kind of conformal theory which lives on the boundary, on a fractal boundary? Like, how do we describe such a theory? It would be interesting to consider that. And we have not really discussed Euclidean or spherical buildings. We have not thought about them, but are they also, can they be holographic? What kind of properties do tensor networks on such buildings have? For example, the p-adic tensor network is actually technically a Euclidean hyperbolic body. But you can think of it as a special case of happy tensor network, but it's also by definition of Euclidean hyperbolic, buildings, it's a Euclidean building. And Gromov hyperbolicity actually plays an important role in the background of all of this. And it's very useful in this discrete setting, but and it's actually secretly also involved in the p-adic setting. But we don't really use Gromov hyperbolicity when discussing continuum ADS CFT. So that is also something to think about. Okay, yeah, that's it. Thank you. Yes. Yes, I mean the toy version of quantum Ryuta-Kenagi, that the entropy on the boundary is entropy in the bulk plus the area law, and then but I think we also want complementary recovery, which is that if you start from a boundary region, you get some minimal surface. If you start from the complementary boundary region, you should get back the same minimal surface. So this is kind of related to sub-region duality, that you can have bulk degrees of freedom which only depend on, well, I mean, there is quantum error correction, but you can just rely on this knowledge of some small subset of boundary and not care about if somebody kind of erased the rest of the boundary or not. So those are all, it does not involve, I think, the JLMS formula though. I think that I think to go to JLMS, you have to actually go beyond tensor networks into algebraic formulation. So you have operator algebras, and then you can talk about JLMS as well. But in tensor networks, you cannot.
So you think there is the right answer,
So you're saying that if we start with, say, H5 or H4, like a time slice of ADS5, this is a toy model in the end. So I don't think it can help you calculate answers in a real string theory, but it can tell you about holography and you can learn more about holography. I think I think of these as just toy models, not something which can give you a realistic, some real theory. Yeah. Boundary dimensions which are integer. Yes. Yeah. Yeah. So those the restriction on n, you can lift by more general buildings, and then there is no restriction. N can be integer, fractal, anything. Yes. So that is the Gromov boundary at infinity. That is the conformal boundary. Now it's not, maybe it's quasi-conformal, I don't know, because it's not the full conformal group which is preserved, but that's the boundary where you expect, the holographic duality to hold. Like that boundary knows about the bulk and vice versa. Yeah, I think you can do that on, I mean, we did that in the p-adic case. You can have general stabilizer codes. I think there's something called the CRSS algorithm, where you start from some classical code and then you generate a quantum error correcting stabilizer code. Actually, there are generalizations of stabilizer codes. And those are more general than perfect tensors also, but they reduce to perfect tensors for special choice of parameters.
Hello. Thank you, Ayan, Suresh, and everyone for arranging this nice conference. So today I'm going to talk about some work that is based on a paper that I have written last year, but much of it is basically ongoing work, so I thought it would be nice to discuss about it here. The talk would be on near horizon, okay, it works. Near horizon dynamics of near extremal black holes in theories of gravity, where we also have higher curvature terms. So I'll tell you why we are interested in looking at the effect of higher curvature terms as I'll go on, and I'll also tell you like what are the interesting open questions that are here. So I also apologize. I have given this talk couple of days back at ICTS. If any of you have heard it, you can leave. The plan of the talk is following. I'll tell you first about some recent developments in the context of near extremal black holes, and then I'll tell you about what kind of what exactly is the theory, in which theory I am looking at the near extremal black holes, how the higher curvature gravity is going to change the basic solutions, and then how I can look at these systems in an effective description, and then I'll tell you how one can go ahead and do the exact function computation for this. Then I'll end with some interesting discussions and open problems. And please feel free to stop me at any time. Yeah? Good. So let's start. So we all know that black holes are really, really interesting objects. I mean, these works are going on, and still there are so many puzzles that one has to solve. So this will, I think, remain a very interesting topic of research for many years, and so far we have a very well understanding of extremal black holes. At least for a class of extremal black holes that arises in string theory, we really understand their thermodynamics well, their entropy well, the statistical understanding of the entropy well, and all. So I mean, there are many works by, starting from Shanmugapriya, then by Atish, a lot of work by Sen, many works from Suresh, and then Justin and Nabamita. So and I think some students also from here are working on this topic. This is really interesting, and we understand extremal black holes relatively well. I just, yeah, I can't. Sorry, I just can't do it. Okay. So now the question is that not only, it's not true that only for extremal black holes the understanding is well, even for non-extremal black holes, whether black holes with finite temperature, even for some of them, some understanding of their entropies and first corrections to entropies are going on. So the question is that, okay, some part of the quantum corrected entropy is understood. What about the full quantum entropy of non-extremal black holes? Because after all, we would be interested in understanding Schwarzschild, right? Which is definitely not extremal. So the question is tough, difficult, and we really do not know how to answer this question in the context of a generic non-extremal black hole. So let us take a baby step and ask this question: that what about the near extremal? Can we understand the quantum entropy of a near extremal? What is a near extremal black hole? A near extremal black hole is which is near to extremal. That means it has temperature but very small. So you can think of this system, and I will convince you throughout my talk, as a perturbation around the extremal system, and then try to understand with our knowledge of extremal black holes more about that system. Okay? So these are the questions. This is the prime question that we are interested in, and there has been some very good development in this direction. Particularly, the first one is important. So it has been said that J2 gravity, which is a 1 plus 1 dimensional gravity coupled to dilaton, only when it is non-minimally coupled to dilaton, it's an interesting case.
Sorry to interrupt. They are saying for the recording, it's important that.
Okay, I'll try. Okay, so so they say that, it is conjectured that JT gravity can actually give us a good understanding of the near extremal dynamics of black holes, at least in the context of two derivative gravities. In fact, as I'll tell you, first, if we just do a semi-classical analysis, we can understand that the semi-classical analysis will tell us that there is a mass gap between the extremal and the near extremal black hole. I'll explain this. But as we will understand that in the region where this mass gap is important, the semi-classical analysis does not make sense. One needs to go beyond semi-classical analysis, and that's where JT helps. That's where this effective descriptions helps. It helps us to perform analysis which is beyond semi-classical analysis, and then we can understand that how the mass gap issue can be addressed in this context. And using this 1 plus 1 dimensional picture, we can actually compute the logarithmic corrections to extremal entropy. So just want to say that here, by logarithmic corrections to extremal entropy, I mean logarithmic corrections proportional to temperature, which is different from what Sen has computed earlier. Okay, so we'll see how these things come. Okay. Now, so far, whatever I said is in the context of two derivative gravity. In particular, this conjecture is very nice and it's very strong. It helps us to do a lot of computation. So a question that really comes is, what will happen to this conjecture if we have higher derivative terms in my theory? Okay, so if I am thinking of now black holes in a theory which is perturbatively away from Einstein-Hilbert gravity, then how is this entire effective description going to be affected? So I'll discuss that. And the study is important because we know that higher derivative terms in the context of extremal black holes really plays a very important role. I mean, for a certain class of extremal black holes, if we do not take these higher derivative terms into account, then we do not get non-zero entropy. So they are important in the context of extremal black holes, and we want to understand that what would be their role in the context of near extremal black holes, particularly when we are interested in understanding the 2D effective picture. Okay, so we'll study this and I'll tell you about the results in this talk, and I'll tell you that it is effectively described again by a JT-like theory with a particular higher derivative modification that I'll show you what it is, and then we'll tell you that when this term is included, how the entire description goes through and what is the corrections to the thermodynamics. Okay, so that's the rough plan of the talk. If you have any question at this point, you can ask. Sure. I will do that. No, so for the bulk of the talk, I'll do that. Just at the end, I'll tell you something else where I'm not doing that. But for the major part, I mean, maybe the 80% of the talk is based on a dimension reduction. Is a 2D perspective here. So the effective description comes when we do dimension reduction. But then at the end, I'll tell you that what if we don't do that. Okay? No. You asked the most important question. I'll come to that at the end. Okay? Yeah. Okay. So let us start. So the near extremal black hole theory that we are going to work with is very simple. It's just simply Einstein-Hilbert action. With I am working in asymptotically ADS spacetime. That's what this L is. This is the cosmological constant. But this entire description can actually go through for an asymptotically flat black hole. So very well we can think of L to be infinity and the entire analysis goes through. One has to take the limit properly, but other than that, it's fine. So we are interested in studying this theory with Dirichlet boundary conditions on my metric and a Neumann-like boundary conditions on the gauge field. So to take care of that, we need to add appropriate boundary terms to the action, and also to avoid divergences, one would have to take the counter terms as well at the boundary. Okay. So when one does that, what one gets is just a simple asymptotically ADS Reisner-Nordström solution. Now, this solution in general, I mean, one can write it down for at any finite temperature T. In particular, if we are interested in understanding the extremal black hole, that is when the temperature is vanishing, or in a more physical way to think of it is when the two horizons are coinciding, then one can show that the near horizon geometry is just simply given by space-time, which is just a cross product of ADS2 and S2, where the radius of ADS2 is this and the radius of S2 is this. In particular, just notice that if it is an asymptotically flat black hole, if the L is infinity, then both phi naught and L2 are identical to RH. Okay, that's the position of the extremal horizon. So that's the simplest geometry that we understand very well. And in this talk, we are going to write every other thermodynamic quantity in terms of charge and phi naught. So charge is always fixed for me at the boundary, and other quantities I am going to express in terms of these two data. Okay. It's at the boundary, right? And then it would be under all large gauge transformation. Sorry, under all small gauge transformation. There is no dilatant at it. It would be. Yeah. Right now it is just like the radius of my S2. Okay, fine. So now, as I said, we are interested in not the extremal system, but in a near extremal system. So how would I go to the near extremal system? The way I am going to go to the near extremal system is following, that we are not going to change the charge at all, as I fixed it from the very beginning. Now I'll just change the mass a little bit above its extremality. At extremality, mass and charge are identical. Right? That's what the condition gives me. But now let's just take it little higher, make it little higher than the extremality. Then what that does effectively is, it changes the radius now from extremal radius to both the radius I'll get, as it is natural for Reisner-Nordström. I'm calling that R plus and minus, where this delta is a parameter again, which is proportional to temperature. Okay. This result is true only when the temperature is small. Okay. Now with this much of data, one can just go ahead and compute the semi-classical thermodynamics. What one finds is that the energy gets corrections above the extremal mass by this amount, whereas the entropy gets corrections by this amount, where this quantity m gap that I have written here is just a parameter which is combination of my other parameters. Okay. Now this point is important. Here is where the first hint of some non-triviality comes. So notice that if we are interested in working at a temperature which is so small that this quantity T naught times m gap inverse is much less than 1, then what it is going to do for me is the E would be m naught plus a quantity which is less than T. Okay, and hence the system cannot have enough energy to Hawking radiate. Because for Hawking radiation, it should have the temperature at least equal to T. I mean, the change in the mass should be at least m naught plus of the order of T. Here it is less than T. Now, this fact will not even change if this quantity, if this is an equality. Even if this is an equality, maybe one quanta can go out, but after that the same problem will arise. Okay? So, then how do we understand it? So, the way people thought of this system is that there is a mass gap. There is a mass gap between an extremal black hole and the nearest near extremal black hole, and if that mass gap, I mean, if the quantas do not satisfy that, then there is no extremal, there is no near extremal black hole. On the other hand, if we just think about it physically, it seems weird. I mean, why do I need to have a Reisner-Nosdorf black hole with, why can we not have a Reisner-Nosdorf black hole with as small temperature as I want? Should be, right? So it hints that there are certain issues and we need to understand these issues. So the way to understand these issues is to question the semi-classical analysis. This conclusion we reach to from the basis of this analysis. But what if in this regime we cannot just depend on semi-classicality? What if the quantum corrections are important in this? And as we will see, it is important in this temperature regime, and that's what we are going to do. Okay. So at this step, all we can say is, let us just compute the Euclidean path integral for this geometry with the fixed boundary condition that we are doing, and try to understand what would be at least the one loop corrections to my entropy. Now that will tell me if those corrections are really important when the temperature is in this regime. Okay, so that is what is going to be the goal of the talk. So we are trying to compute the one loop corrections to the semi-classical results for near extremal black holes in this theory. Is this okay? Any question? Okay. So, yes. How should I think about? So far this analysis is considered, M gap is nothing but this combination. So far it has no physics attached to it. Okay. All we can say is that whenever this, so this is a parameter of my theory, which is definitely non-zero. Okay, and temperature is, I am introducing non-extremality to my system by making my mass little higher than extremality, and all that is telling me is that whenever that temperature is satisfying this condition, even with the equality, I have a problem with semi-classical analysis. Okay, I mean, we would prefer to say that the problem is with the analysis and not with the system, right? Because as I was saying, I can have a Reisner-Nosdorf black hole with as small temperature as I want. So let us try to understand, let us try to make our analysis better and see if we can get out of it. This is purely semi-classical result. Just compute the action on shell, taking care of boundary terms and other things. Yes, okay. Yeah. So I'll tell you that mass gap is not, higher derivative is not going to solve this problem. We need to go to quantum, we need to consider quantum corrections. Question comes, in presence of higher derivative, how can I compute that? How easy or difficult it's going to be. Okay? Yeah, so all the things that I'm so far talking about is like very well described by Trivedi et al. And Turiachi et al. Okay. So now let me go. Is it okay? I'm going ahead. Okay. So as I was saying, what we would be doing would be a modification compared to the theory that I just showed you by this bunch of higher derivative terms, which are to begin with just 4 derivative terms involving curvature. But again, at the end, well, if not at the end of the talk, you can look at my paper. The analysis is going to be valid for all 4 derivative corrections involving metric or gauge field. The analysis actually extends to all. So let us just for simplicity start with this. I have taken a particular combination as Gauss-Bonnet because that just simplifies. We know that in 4 dimension Gauss-Bonnets are topological terms, so it will basically do nothing, and all the results will actually depend on alpha 1 tilde and alpha 2 tilde. Okay. Now when we have higher derivative terms in my action, the boundary terms also needs to be modified. So that is what I have given here. I must tell you that this correction to the boundary terms are only correct perturbatively in lambda. So this term is also perturbative in lambda. Okay. Good. Okay. So first, let me just write down the extremal background, which is going to be corrected from. Okay. So I just demand that the variations are well defined even in presence of these things. Okay, but then I want that boundary term should only make sure that variations are well defined up to order lambda. So terms that are going to be no. So no. If this if I am just writing this as my bulk action, then there I don't need to consider lambda to be small at all, right? Right. But the next statement is that here, when I am writing this as my boundary terms, this will only make sure that 2 order lambda the variations will cancel. If I am taking okay. So let me write down the extremal background. Again, the extremal background will have this near horizon geometry as ADS2 cross S2. Only difference that it's going to bring is that the parameters are now going to change. Okay. So the parameters will, if you remember, the radius of S2 was phi naught. Now it is going to be corrected by an amount like this, and the radius of okay. So basically the ADS2 radius will also change such that R tilde now becomes this. So that is how it's going to change. The charge will remain same because we are fixing that, and other quantities one can now go ahead and compute for this system. So this can be done using sense entropy function formalism. Very simple algebraic equations one has to solve. Only non-triviality that one needs to keep in mind is getting this relation here that I showed you. The boundary terms needs to be proper. But once that is taken care of, the other part is not difficult. Okay, good. So now, as I said, all we want to do is we have this system whose extremality looks like this, the system at near horizon at extremality looks like this. We want to understand what would be the first one loop correction to its entropy. That's the question. Okay. Good. So now to answer this question for next couple of minutes, let's forget about the higher derivative. Let's just ask this question in the context of 2 derivative gravity itself. Once we understand that, it has to be extended for higher derivative gravity, but that's a technicality and it can be done. Okay. Now, in the context of 2 derivative gravity, let us first make a simplification and say that we are only interested in spherically symmetric geometries. Okay. So now, for all such geometries where I have a S2 symmetry, the most generic way I can write down the metric would be something like this. Yeah, I understand. I am just forgetting. It is something like this. So every fields are going to be only functions of coordinates on the first 2 part, r and t. Nothing will depend on theta and phi. And this reduction, if we reduce the theory on the S2, this reduction will give me an effective 2-dimensional theory. This is what you were talking about, which will now have dynamical fields as graviton. The dilaton, I mean the scalar field that's basically acting as the radius of S2, and then bunch of gauge fields. One gauge field directly coming from the gauge field in the higher dimension, and then other SO3 gauge fields coming from the reduction. Okay. So I will have a non-trivial theory with all these things, and the theory will look something like this, where u tilde phi is a potential of phi, and u tilde phi does not involve any term to 2 derivative gravity that involves any derivative of phi. In fact, the whole reason of this Weyl transformation was to make sure that here in the 2 dimension I do not get a kinetic term for dilaton. That's all that it does. Okay. Now you can think like, why am I doing this? It would be clear a little bit later. But this is what we get. Okay. Now what is SH here? SH would be the kinetic terms that will involve these gauge fields, and I have not written it here because Again, that just complicates the whole system, does not really change physics much. And if we can do it for systems where there is no such fields, I mean basically where there is no non-trivial angular momenta in my system, then it can again be extended for non-trivial angular momenta sectors. So for the timing, let's even forget about this. This is just the basic reduction from 4D to 2D that we will get. This is the bulk part and this is the boundary part. Capital U. Capital U is a potential of phi. So it will have constants, like the cosmological constant can appear here, and all combinations of powers of phi. So see what did we have in the parent theory? So let's forget about these pieces. Okay, in the parent theory I had square root g r and 6 by L square. I also had this piece in the boundary. Now when I am dimensionally reducing it, I will have and doing a wild transformation it will bring in various factors of phi. So all those factors of phi that where there is no graviton involved is incorporated in U tilde phi. I have, the expression is given. I have just not written the details. What is? Oh, so this, when I am reducing it over the spherical harmonics, I need to take their effects into account. So it will be this. So basically, when you are non-trivially reducing on the S2, how you have to do it, that entire details is involved. F square is there. No, so SH is non-trivially, so SH is the part that is coming from the gauge fields, which is basically due to reduction. Okay, so that is, those part I have kept in SH. This F is the part that is directly coming from my gauge field in the 4th dimension. I can integrate all of them out, just in the next slide. Yeah, I can integrate all of them out, yes. So as Chetan rightly pointed out, this is a theory in 2 dimension, and in 2 dimension gauge field strength is trivial. Right? It has to be proportional to epsilon mu nu. So using that fact, one can integrate it out, as he was saying, and the effect, sorry? Yes, there is a dilaton in front, but even then, U tilde will change, exactly. Yeah, U tilde will change, and what you will get is, that is why I wrote U tilde there, you will get a different potential now, which will have the effect of the gauge field also into it, and this is what you are going to get. Okay, but at this point, please keep in mind that this U phi is a non-trivial function of phi. Okay, it involves powers of phi. Is this okay? Good. So this is the 2 derivative description that you asked me at the beginning. Yes, so if we are interested in understanding spherically symmetric black holes, then we can do this, and this is the effective theory with what we can work to find the corrections. Okay. Now the question remains that how do you do it? Yes. You mean the constant phi naught? Yeah. So in U phi there are phi naughts. Yeah, but that's like not a field for me. So all those effects I have put them in. Okay. Now a small term to add here is, how will this expression change when we have higher derivative terms? So if we now work with the full action that I showed you, I am going to get this, but then with this many other terms, which all of them are proportional to lambda, and they can now involve derivatives of phi as well. But all these terms are going to be proportional to lambda, and you can find the details in the paper. But that's how this action is going to change. Okay, good. So now, as I was saying, so I know what my effective system is. So far, we have not done any simplification. It's just direct dimensional reduction, and only one simplification that I have done is I am working with L equal to 0 sector. But as I said, if you want, you can work with the, you can keep the L equal to 1 term as well. Life would be a little bit more complicated, nothing else. Okay. So Now, how are we going to compute the quantum corrections to entropy for this system? That's the question. Sure, go ahead. Yes, so that's what this line is. At higher derivative orders, we get various 4 derivative interaction terms involving the scalar and the derivatives of phi. Okay. So my higher derivatives that I started with, so this statement is very specific to the higher derivatives that I started with. That was only R square, RAB, RAB and RABCD, RABCD. Okay. Up to 4 derivative, only derivatives involving metric. Right. Now the metric reduction, I am working with L equal to 0 sector, so you can forget about curly A for the time being. These guys you can forget about. Okay. So now this R square, RAB, RAB and RABCD, RABCD is only going to get contribution from this and this. Even if you don't have while scaling, let's say I don't have while scaling, all it can give me are 4 derivative terms involving G and phi. Okay. Now because of while scaling, some of the terms will go, some of the terms will get modified. This while scaling really does not do anything in favor of me or in not favor of me at higher derivative level. All it does is a favor to me at 2 derivative level, and that is it kills the kinetic term of the dilaton. Okay. So now let's ask this question, that how are we going to address this problem? The way to think about this is following. So this is my effective theory, right? The one that I just showed you. It's going to have some geometry. I'll have certain geometry for this. Let's just split that whole geometry into 2 regions and call them as a near horizon region. As the name suggests, that would be the geometry when we are going to the near horizon, when we are zooming to the horizon of these near extremal black holes, and the other part is what I'm calling to be the far region. Now when we are at far region, of course we can think of the geometry to be as extremal geometry only, right? Because at far, the effect of the source, that is, the effect of the change of the mass above extremality is going to be very small. So at far region, geometry is well understood. At near horizon region, the geometry would be non-trivial. But the way I can think of this entire computation is to do a computation around the near horizon region and do a computation in the far region and then sum them up. Okay. Now when I say this, I need to tell what do I really mean by near horizon region. Up to how far my space, I can approximate it as near horizon region. So that brings in a effective boundary description to this system, which was not there to begin with. Am I making myself clear? So I'm just saying that the whole space I'm splitting into 2 parts. Now as soon as I'm splitting it, I need to bring in a boundary into the picture. Let me call that boundary as RB. Okay. Now please understand that this was not there, and we have, like, just for our possible way of computation we have this. So only thing we need to make sure that every field is smooth at that boundary. Okay. So with that condition, with that kind of a splitting in the geometry, let's try to do the computation and see what we get. If you have any question at this point, you can stop me. It should be, because it should be in the near horizon geometry, right? So it should be something more than, in fact the horizon right now is already higher than RH. So it should be of course greater than RH. This is the definition of my near horizon region. Yeah. Okay. Good. So then what we want to do is we want to compute this partition function of this effective 2-dimensional theory. And all we want to do is we want to compute this action now as, I have to integrate it over my whole solution. All I am doing is I am just splitting it into 2 parts. And to begin with, all I am doing is I am saying first part is I am integrating it from RH to RB, and the next part I am integrating it from RB to infinity. So if you just take these 2 and add it up, it's basically the action that I started with, nothing else. Okay, and this is the usual boundary term that I already had, which is basically at the asymptotic boundary. So this is all that I have done so far, and this is like nothing new or nothing added, that nothing extra that I have added here. But what you can show is the effect. This requires a bit of computations, and I am not showing it here. What you can show it, that the effect of this far part is actually to bring in the boundary term for this part at this boundary. You can do this computation. I mean, this is actually can be done covariantly. If you do the covariant computation, you can show that up to divergent pieces, which will anyway be taken care by the counter term. So let's not talk about them right now. The effect of this far region is exactly to bring in the appropriate boundary term for the near horizon region. No, so total action does not depend on delta. So you mean, oh sorry, you mean after computing this? Yeah. So it does not depend on the value of delta V. It does not. The whole analysis will be independent of that, but it is important that there is a boundary. It does not look like that it is manifest. You have to do the computation and then only it will run out to be. Well, right now there is no delay. I mean, so by dilaton gravity, do you mean JT? Right, yes, that's correct. So I agree to that statement, yes, but here what I am trying to say is, following. We wanted to do this quantum path integral computation for this system for the near extremal geometry. What we have been able to show is, to this point, that the computation just boils down to the near horizon geometry of that. That's the statement. Okay, to the same action, the same boundary term, but now I can forget about everything from the far region, just concentrate on the near horizon region, and that's what is going to give me the contribution to this action. That's the statement. No. Boundary condition. Oh, sorry. Boundary conditions is very important. As I said, that we want all the fields to be smooth at the boundary. So at this boundary, the metric is going to be Dirichlet and a Neumann boundary condition for gauge field, appropriately in my geometry. At the asymptotic boundary, yes. Right. It imposes Dirichlet boundary condition at that boundary. Yes. What should? At the end of the day, when you will compute the full action, and that will be independent of delta RB, given the partition function. Any other question? What it would not be independent of is the boundary values of my field at delta RB, but it would be independent of delta RB. Okay? So here when I am doing this analysis, I am saying that, okay. So let us understand then how the statement that I have just made, that this quantity, the effect of this term is effectively a boundary term here, how that comes. So all I am doing, I mean, basically making a 0. So I am writing a 0 as plus a term which is exactly the boundary term for this term minus the same term. Okay, and then and now that I have a boundary, so I have to definitely tell what is the boundary condition at this boundary. The boundary condition at this boundary, all I am demanding it's smooth from both sides for my metric, and the dilaton is also behaving as it should behave at the boundary. Okay, which basically goes as, well, we need to find the solution and write the boundary behavior. When one does that and then compute this far region action along with that extra piece, you can show that all it gives is a pure divergent term that can be taken out by the counter term. So as I said, there is a of the boundary. I'll tell you what it is. Okay. So now I have my, I understand what my action is going to be. So next step is to basically go ahead and compute the one loop corrections to my actions. And the way I'm going to do this is again for both. Now I only have the NHR region. So the NHR region, I'm going to fluctuate around my background, where the background is just the extremal background. I'm going to fluctuate around the background, and then I'm going to write down the final action to quadratic order in the background. So this you don't have, you have to imagine this is my whiteboard. So the space is like this. Okay. Only difference right now is that since it is near extremal and not extremal, so the throat is not infinitely long, but it's finitely long. And then I'm just putting my boundary somewhere. Doesn't matter where you are putting it. There is going to be non-trivial effect only coming from the boundary. I'm going to tell you about that. Absolutely. Okay. Now this action that I have written down here is just up to, this is a linear action, okay, just up to the first order terms in phi and my metric, and then there remains the second order term that I have not written. But notice, epsilon is a epsilon. So epsilon is like this. I'm sorry. This epsilon is the bound. Okay, I'm very sorry. Maybe in the next page I have written it. Okay, so this epsilon is the boundary. Okay, good. So now notice one thing, and that's again nothing special to this particular system. That if you have a system, and if I am fluctuating around a classical solution, then to linear order I cannot have any non-trivial term. It's zero. Okay? Then all the linear order terms are zero just because the background will satisfy the equation of function. And that's what you see from here. Although I have written down the R here, but this R is supposed to be computed on the extremal background, and that will make this term vanishing. Okay? So the only non-trivial term that remains here is this piece, which is a one-dimensional term. And all the non-triviality to linear order to this action is only going to come from this term, which is a boundary term. So we need to understand how to compute that term. Okay, other terms are higher order in phi, and of course they are important because they are only going to tell us how my dilaton and how my background is going to be corrected. Is this clear? Okay, good. So as I wanted to emphasize that the linear action term is just an appropriate boundary term in the NHR region. So now let's just compute it. So to compute it here, I have just given a little, sorry, so Suresh, this is what I was saying. Please excuse me, this is just small fluctuation. Think of it as epsilon. And all the changes here that you can see, the tildes that I am talking about, is the appropriate quantities that I just showed you, but now taken the higher derivative corrections into account. So if you do this calculation now for the entire higher derivative term, all it is going to change is it's going to change the constants. Once you take that into account, then this is how it's going to be modified, and we are doing the similar analysis but in a modified background. Okay, and the effective one dimensional action that you get is this. Okay, for just two derivative gravity it was square root h phi k, but now in presence of the higher derivative terms that I have started with, it gets also these two corrections. So that is what the final action, where this k needs to be computed on ADS2 background, but keeping in mind that there is a non-trivial boundary, and from the boundary one will get the boundary graviton contributions. Okay, and other fields one can find it out. It changes the near horizon geometry, and that's very important. I'll come to that at the end. And then if one goes ahead with the calculation, so basically it's like this is how people say that it's like effectively given by a JT theory. Although what we will probably be thinking about is that it effectively gives us a boundary one-dimensional action, and that boundary one-dimensional action governs the entire quantum entropy computation. I mean the quantum computation of the system. So with appropriate choice of constants, one can show that action just boils down to this. Okay. So what are these modes T's? These T's are the modes on the boundary. So the space in the bulk, I mean, we are in the NHR region with a boundary at delta NHR. And now in that boundary, the modes are like some TU that you cannot fix. These are like large gauge transformations for your system. And what the effective partition function looks like is just a Schwarzian for that. Okay. This again requires a bit of computation. I'll tell you how it comes. So there is this K involved, right? So we need to write down this K on my geometry with the boundary condition. It will bring in certain divergences that can be taken care by counter terms. Once you do that, then the modes just, then the action just looks like this. I was fast. You mean for higher derivatives? Yeah. Why such term should not? Sorry. What is your question? See, I am not writing down this Schwarzian. I am getting this Schwarzian. Because I am restricting myself to linear order in fluctuation around background. And the statement is only linear order terms around background governs the near extremal geometry. Then that's it. Okay. Now, as I was saying, that basically so far our analysis gives us this Schwarzian. So far there was no jetty gravity. What we get is a Schwarzian. But the parallel statement is for 1 plus 1 dimensional gravity theory, particularly for jetty gravity theory, the dynamics is governed by a Schwarzian. Okay. So these two statements put in together, one can think of that the near extremal dynamics, the near horizon near extremal dynamics is also governed by a jetty gravity. But this statement is not important for the rest of my talk. All I need is what we got, and that's the fact that there is a Schwarzian. This integration is over the boundary. So this is SL, I mean this is modded. So yeah, so basically in the bulk you still have SL2R isometry. You can show that the diffeomorphisms which are non-trivial are those which are not, other than the SL2R. SL2R will still remain as a, because your background is still extremal, no? And that has the SL2R isometry. I am fluctuating around it. So the prime part of the isometry will be there, but all you have right now is a boundary, and whichever diffeomorphisms are non-trivial there is going to contribute, and that's why you have to mod out by, so these are all those diffeomorphisms modded out by the bulk symmetry. So no, I don't think it is no, it is not negative. It is not negative. This phi b is the boundary value of the dilaton, which would be related to the temperature. Z beta would be proportional to it. It will give you the temperature dependent corrections. Yes. It is 8 minutes. Okay, fine. So basically, all we wanted to understand is motivated by this fact that a Schwarzian corresponds to jetty. We wanted to understand that for our case, where the one-dimensional action, if you remember, had a correction proportional to higher derivative term, what would be the modifications to the jetty-like theory that will give me this? Okay, and since I do not have time, I'll just tell you what the results are. You can find out the corrections to dilaton. You need to correct the basically the bulk part of your jetty gravity by appropriate term, but keeping in mind that to leading order, it should always give me back the corrected ADS geometry in the near extremal, corrected because of temperature, and the higher derivative terms needs to be taken into account such that I get the right boundary term. Okay, so this term is what we had to find, and such that we get this as the full action, where this part of the action we already knew, right? I'll just show you. Just give me a minute, because Yes, this is what we found. So I wanted to modify my JT such that I get this, such that this should be the right boundary term. This should be the Schwarzian for me. So that is what we did. Okay, and the corrections is this with appropriate choice of these two constant V and Z that I am going to tell you what they are. So yes, this is what your Z should be, and other constants are like this. So what I wanted to tell you is following, that the near horizon dynamics of the near extremal black holes which are spherically symmetric is basically governed by Schwarzian like action. These statements remains true even in presence of higher derivative gravity. We have checked it for 4 derivative gravities. I think it would be true perturbatively for any other higher derivative gravity, but all that requires for this to work is to correctly modifying your JT theory with appropriate higher derivative terms. And to 4 derivative level, now this is a result that I am just telling, to up to 4 derivative terms, be it involving the metric or the gauge field, the only higher derivative term that you need is R square, and that's it, nothing else. Okay, all that basically you have to find are what this function, this quantity is, what this Z is. Once you identify the that parameter, you will get it for any. So basically the upshot is that it works when I have perturbative corrections in my theory. Okay, that is what I have said, that in when you take that into account, the effective Schwarzian changes with phi just replaced by phi tilde, where phi tilde is the appropriate corrected one. And once I know phi tilde, one can just, once I know this partition function, we can just go ahead and compute the entire thermodynamics, the one loop corrected thermodynamics, where the change in energy, free energy turns out to be this, change in energy turns out to be this, and change in entropy turns out to be this. Okay, any questions so far? Okay. So thus basically the whole story, which was already established by Sandeep and Turiachi. Primarily these two papers are very, very nicely written. So there are many other references. So the whole story actually nicely and non-trivially works in presence of arbitrary 4 derivative perturbations in the 4-dimensional theory. As I said, all it requires is to add a R square corrections to JT gravity, and we found the corrections to the entropy here. Now there is one statement that when I started with, all I wanted to compute is just one loop corrections to my thermodynamics. But when we found the Schwarzian and we understood that Schwarzian basically comes from a JT-like theory, there the result is actually one loop exact. So these results are actually exact results. So these are the full quantum corrections to your entropy and all other thermodynamic quantities. Okay. So that's basically the prime result. But now I want to go to an important discussion, and the discussion is as follows. See, please notice the expression of the entropy. As you can see that it now involves a log term. For entropy, it's primarily important. It involves a log term involving temperature. Okay, and the other quantity is phi tilde b, which is basically the boundary value of this dilaton. So now, if you just scale these quantities as I have written below, you can always show that this correction to your one loop entropy, exact entropy actually, turns out to be a log of these 2 dimensionless parameters. And they can be actually made as small as you want. Right? So which basically it is telling me that something is not correct because the entropy is getting now a large negative number. Okay? But I just want to tell you that this is, I should not have probably talked about entropy from the beginning, because what you can compute for this system is the density of states, and the density of states looks like following, and you can show that when your temperature is vanishing, then the density of states is itself vanishing. So for systems where density of states are vanishing, entropy is not even a right physical quantity to look at. So the conclusion is following, that there is no problem to the fact that delta S is negative. Delta S is not a physical quantity for this system. The system is absolutely fine. Taken quantum corrections into account, I can go to any small temperature as I want to. Only thing that it does is when the temperature is very, very small, the density of the states for this goes to 0. Okay. So the problem that the semi-classical physics posed to us, that there is a mass gap, is not really there when one takes the quantum corrections into account. Okay. And yeah, basically a solution to this problem was proposed by Almeri and Polchinski, and is also correct for supersymmetric theories, is that there is a mass gap which naturally arises when you have supersymmetry. But when there is no supersymmetry, this mass gap is not there, and that's not a problem. This is what I want to just emphasize. Okay. But let me first, how much time do I have? 2 minutes? Okay. So conclusion is something that I have told you many times, so let me skip it. Okay, because I want to tell you something interesting. So what is next? Okay, see, the fact is, all we have done here is based on this effective description of the system. Okay, that I can integrate over the sphere directions and then can go to an effective theory, which up to linear order gives me a Schwarzschild and then back. So we really have not, all we have seen is that there is a Schwarzschild, and then we said that since there is a Schwarzschild, there must be some Jetty kind of a description, and hence this result should be quantum. Which is a very, to my thinking, is a very roundabout word. Rather, what one should be doing is a direct analysis for this system from 4-dimensional perspective. Okay, so just compute this. So the question that we can ask is like, what would be the corrections? Let's just say one loop corrections, so just a logarithmic corrections to near extremal entropy from a 4D one loop partition function computation perspective. Okay, and that's what we are trying to get to. We are very close to the results, but I'll just tell you some highlights of it. So again, the way we should be thinking about is in terms of a near horizon region and the far region. Split the result and then try to get it, but now not in the context of 2-dimensional gravity, but in the context of full probability. What we found here, and hence I just want to show, is a very interesting fact. And the fact is, the near horizon geometry is not ADS2. It really gets a correction, it picks a correction to ADS2, and that correction by no way you can bring back to ADS2. So that poses really a question to me that probably mapping into JP was not a good idea. Because it is not ADS2, you cannot do a Y transformation or a coordinate transformation to bring it to ADS2, the reason is simply in the Z. The trace of this part, and no coordinate transformation can change together. So it's not ADS2. Nevertheless, it's not geometry. I can still think of it like the far region is not going to change. That will be extremal anyway. The near horizon region is different. Does not have ADS2 isometry, and hence computations are not trivial. One needs to take care of the boundary terms very, very carefully because they are going to be non-trivial, unlike what they are in Ashok's extremal calculation. Here they are non-trivial. And once they are taken into account, at least the semi-classical result works out. So all we need to understand is how the corrections are, and hopefully sometime in next talk I will do that. Thank you.
Thanks very much.
So Ashok's Schwarzschild computation only holds for finite temperature, and Ashok's extremal computation of course only holds for 0 temperature. So that was my first try. But if one cannot take the small temperature limit of that, cannot be. I'll tell you where the problem is. Not problem. Where the complication would be to find the boundary, which has nothing to do with this. Once you find the boundary term, the rest of the story will come. Schwarzschild. The Schwarzschild form will retain, the prefactor will change. But that prefactor now you need to find. We have to find the boundary terms for it. When it is higher than 4 derivative, it would be higher.
Maybe that's what you're doing towards the end of this new part. You kept only the S mode. What about the closest time mode?
Oh, okay. So, very good question. So, when we balance temperature region so massive that we can neglect to this order. Otherwise, they are. No, yes, yes. At one look around my background, they would be there. So I have to take their contributions also into account. Zero more than also. Yes.
So, I have a question. So, in your, so in the second part of the talk, you said that SL2 symmetry can be broken.
Yes.
But
At the moment.
from the older language, do you understand how exactly this SL2 symmetry
Yes.
is being written?
By older language, you mean dirty language?
In the dimensional reduction.
Yeah. So the SL2 is broken explicitly when I'm bringing in the boundary into mind. So in the boundary, now I do not have full Virasara. I only have time reparameterization, which is time I'm saying because I denoted as Q. In fact, you can actually show that it's basically coming from the time is reparameterization of the ATS. So only time reparameterization symmetry remains, and that's what gives you finally the Schwarzschild. But the full Virasara symmetry is good.
You mean full SL2 is good?
SL2 is in bulk. In the boundary of ADS2, you have more symmetries. So SL2 is there. But the other part of the Virasara, the Virasara is infinite dimensional symmetry.
Yeah, but the Schwarzschild action has this SL2 symmetry, which is not there, which is broken.
No. I am saying, no, SL2 is there. That is why I am modding out by all those modes which are just coming from SL2. So I am only integrating over the modes which have broken full Virasara to time reparameterization, keeping SL2 in there. That is why I am modding out by SL2.
No. My question is, you said that the ADS2 background itself is corrected.
Oh,
I was talking of how you understand that from the older picture.
okay. That's, yes. Do you give me 2 minutes?
Yeah, sure.
I'll tell you how it should come. It comes from here.
I see.
These terms I need to keep. They will correct my background.
So these you neglected because you were looking at
I'm only
linear fluctuation. So non-linear fluctuation. So then comes my next question is there a way you can characterize this as something parametrically as some soft breaking of the system?
Maybe it is possible. See, right now my only intention is to understand how to get this result and get to the right result. Let me say, maybe this is also right. But get to the result in the right way, directly from 4-dimensional structure. Once we see that picture, my job is to basically see how it is going down in the effective distribution. Because so far, to this page, right, there was no, I didn't make any approximation. This is not really effective other than the fact that mass is more faster than more than mass. Other than that, it's completely exact. So once I see that picture, I should be able to answer.
Okay, one for final question.
So while doing this dimensional reduction, where did you put like formation of unidirectionality?
No. The dimension reduction goes for any spherical symmetric circle.
Again, only the
It came here.
derivation and
Yeah, it came here. See, here I had this potential which is completely generic. Then I expanded it around the background to linear order. That's where the background that I considered in the near horizon region was extreme.
but then would not it have been done without doing dimensional reduction? You start with the generic dimension clearly and less.
I'm trying to do that, yes. So I think this, the statement that I made, that this piece is only giving me the boundary term is true actually. It's a covariance statement actually. It's true even in 4D. Can retract it. But because your radius 2 is gone, still very hard. Not very hard, hard.
Okay, so we should now have lunch and this thank Nabamita again for the very
This is the title of my talk, Thermalization in Semi-Holography, and it is based on ongoing work with Toshali, Mitra, Ayan, Tony and Alex. So this is the outline. So first I will review the semi-holography. Then I will talk about the thermalization in the in a particular semi-holographic model. So I'll put a puzzle as to why a puzzle of thermalization, and I will give a resolution of that. And then finally I will talk about the quantum case where you have two quantum system coupled with semi-holography, and the thermalization in such a system. Okay, so a semi-holography is a theoretical framework which consistently combines perturbative and non-perturbative descriptions. So, for example, such a framework could be important for understanding systems such as quark-gluon plasma, which is produced in heavy ion collision experiments. So, in heavy ion collisions, the two heavy nuclei collide and it produces deconfined state of quarks and gluons called quark-gluon plasma. Now, this quark-gluon plasma goes through various stages of evolution after this collision, and at different stages. Okay, so usually the perturbative and non-perturbative degrees of freedom coexist in the quark-gluon plasma, and most of the theoretical approaches that describe this QGP produced in heavy ion collisions either stick to the only perturbative or only non-perturbative paradigms. So, the semi-holography is a framework that can combine both perturbative and non-perturbative in a single framework. So, another motivation is from condensed matter side. So, for example, in systems such as strange metals, also the perturbative and non-perturbative degrees of freedom coexist at some point, and semi-holography can be relevant there as well. So how does this work? So there are two sectors, as I said, the perturbative and non-perturbative sector. The non-perturbative sector is described by some holographic gauge theory, which has some gravity dual, and then we have to describe the system consistently such that the two we have to couple the two sectors, the perturbative and non-perturbative sectors. So this is done by the following. This is done as follows. So the marginal relevant couplings in each of the sector is promoted to the op function of the operator of the other sector. So I will describe this in detail with a particular example later. So such a framework is consistent with Wilsonian RG, by which what I mean is, if we have only low energy description of perturbative and non-perturbative sector, that is sufficient to get the low energy description of the full system. You don't need the microscopic details beyond that energy scale. Therefore, it is useful for building phenomenological models. So if you want a naive guess at coupling the perturbative and non-perturbative sector would be to use coupling of this kind, where you have some gamma as where you add such a term in the action, where T mu is the operator of one sector, say perturbative sector, and T tilde of the non-perturbative sector. For example, it could be stress tensors, and the gamma is some coupling. But such a coupling can become irrelevant if these operators have higher dimension, and it can spoil the renormalizability of the full theory. Also, if let's say this T mu and T tilde mu are hydrodynamic stress tensors, then when you differentiate this with respect to metric to get the full stress tensor of the full system, you will end up with operators which are higher order, which are not hydrodynamic. So just having the hydrodynamic descriptions of the subsystem is not enough to get the hydrodynamic description of the full system. So then the solution is these democratic couplings, so which has been derived in these papers. So these couplings can be of various kinds, scalar, vector, metric, etc. So the idea is what I described before. In this coupling, the marginal relevant operators of each sectors are made functions of the, marginal relevant couplings of each sector are made functions of operators of other sector. So let me describe it with the example of one particular metric coupling. So for metric coupling, this is the action of the total system, where S1 and S2, these are the Wilsonian effective actions of the, say, perturbative and non-perturbative sectors respectively. And we also add these two interaction terms in this particular way, where this gamma and gamma prime, these are the new couplings introduced in this semi-holographic called semi-holographic couplings. And these G mu nu and G tilde mu nu, so these are the effective metrics of the two subsectors. But what I mean is that, say, perturbative sectors lives in this some metric G mu nu, and non-perturbative sector lives in another metric G tilde mu nu. And this G mu nu background is the metric of the where the full system lives in. Yeah, so if you vary this action with respect to this matrix, effective matrix G mu nu and G tilde mu nu, then you end up with these coupling equations that describe the coupling between the two sectors. So notice that in each, so for example, in first equation, this G mu nu, effective matrix of the first sector, is function of these operators, which are this stress tensor T tilde of the other sector, and similarly for the second equation. By varying the full action with respect to the background metric, so this G mu nu, the actual background metric, if you vary the action with G mu nu background, then you can get the stress tensor of the full system, which has this form. So again, this stress tensor is just some polynomial of this subsystem stress tensor, small t mu nu and small t tilde mu nu. So just having hydrodynamic description of these subsectors is sufficient to have some low energy description of the full system. Then given that the subsystem stress tensors are conserved in their effective metric backgrounds, so this first del mu is the covariant derivative with respect to the first metric G mu nu in which the first sector lives, and similarly delta mu tilde is the covariant derivative with respect to the other metric G tilde mu nu. So this, given that the two stress tensors of the subsectors are conserved in their own effective matrix, then this framework guarantees that the full stress tensor constructed in this way is always conserved in the actual background metric. Yeah, so I've described how do we construct the action and the operators of this in this semi-holography. So then how do we actually solve for the dynamics given a particular model? So this can be done using the iterative procedure. So what we do is we solve the equations of each of the subsector, perturbative and non-perturbative sector at each step of the iteration, and use the solution of the coupling equations from the previous step of the iteration. So this is the coupling equations. We have coupling equations and we have the equations of motion for each of the subsector. So at each step of the iteration, we solve both the equations of perturbative sector and non-perturbative sector independently, and use the solution of the coupling equations from the previous iteration. And we continue this process till the iterations converge. So I will describe this iterative procedure by using a particular example, which will make it more clearer. So the important thing is that at each step of the iteration, each subsector is deformed by marginal or relevant deformations, and therefore the full system is renormalizable at each step of the iteration. And it is a priori not guaranteed that the iterations should converge, but they do converge in all of the examples that have been studied so far. We observe that always the iterations converge. So I will describe this by. I mean, whether we can parameterize it somehow. Yeah, so we don't know anything.
So if it doesn't converge, then this whole thing will not. For that kind of thing, this will not work.
So you were saying that it is possible that in some cases it will not converge, and then you will not consider possible.
Okay, so I will describe this iterative procedure by focusing on one particular example. So in this example, we coupled a scalar field with a black hole, or a holographic gauge theory. So scalar field, think of scalar field as a perturbative sector, and the holographic gauge theory at finite temperature, which is dual to a black hole, as the non-perturbative sector. So this is the action of the full system. The first term, where this is chi, is the scalar field, massless scalar field. So that action is that of the massless scalar field, and second is the effective action of this large and strongly coupled holographic CFT. So that will be dual to a asymptotically ADS4 black brane geometry. So according to holographic dictionary, WCFT is equal to the on-shell gravity action with the source small h in the CFT replaced by this phi 0, which is the normalizable mode of the leading term in the bulk massless. So there is also a bulk massless scalar, capital phi. So phi 0 is the leading term of this capital phi. So and then there should be a dual operator to capital phi, so which is this math cal h, and yeah, so the small h is like the source to math cal h in the CFT side. So in this system we have the equations of motion for gravity side, which are the Einstein equation.
Should be g of x to be not h of x to be 1. G is the coupling. The h.
No, h is the coupling. H is the small h is the source. Which is okay. So we have equations on this non-perturbative side, which are the Einstein equations, plus the equation of motion for massless scalar, and then the equation on the perturbative side, which is just the equation of motion of this scalar, this chi scalar, which is the boundary sector. Now, of course, we need to couple the two things. So this is why we have this extra term on the right hand side. So this operator math cal h, which is the CFT operator of the non-perturbative sector, that sources this perturbative sector of chi, and this beta is called is semi-holographic scalar coupling. So previously I was talking about the metric coupling. This is the scalar coupling, and then similarly the phi naught, which is the source of the holographic sector, which is provided by the operator of the perturbative sector, which is this scalar field chi with the source beta. Yeah, just to give some more details. So when you solve the gravity side, we start with some non-equilibrium metric. In ADS4, we work with ADS4. So this is the parameterization of some general homogeneous non-equilibrium metric, and then there are so usually these equations that I showed, the Einstein equations plus the bulk scalar equation, those will be partial differential equations in t and r, where t is the time and the r is the radial coordinate. But then but if you convert the time derivative to this derivative, which is the derivative along outgoing null geodesics, then all these equations become ODEs in this radial coordinate at each time step. So these are those ODEs. So basically solve this set of equation at each time step, and we solve the whole system. And so we solve, and then we get so this operator, this holographic operator math cal h, has this expression. So where phi 3 is the normalizable mode of the bulk scalar and phi 0 is the normalizable mode. So it involves the higher derivative, third derivative of this source. I'm not using the dependence on the spatial coordinate in the boundary. It's only the time coordinate on the boundary and the so bulk, this r is there, this dependence is there. In terms of boundary, there is only time, there is no space coordinate. Okay, so yeah, and on the other side, this equation I already showed. So the boundary scalar equation sourced by this h operator. So to solve, this is how we solve the system. So initially at the first iteration, yes, the math cal h is dual to the bulk scalar phi. So then this is the semi-holographic construction, where if there were no semi-holography, this is just del mu chi is 0. But by semi-holography, so what we do is we source the perturbative sector by the non-perturbative sector. So the operator of non-perturbative sector with this h.
Why do you have to find out?
Why?
We have a formula for h.
Yeah.
So the phi naught. I don't understand the formula for h.
So phi naught is the source for the phi. If you only consider the holography side, let's say we don't consider the coupling with the scalar sector. In that case, this phi naught is the source for capital phi. Now, when we couple the two things, the source of this capital phi should come from the perturbative sector. So that's why this phi 0 is proportional to chi. In the similar way, the source for this chi, which is the perturbative sector, should come from the holographic sector. So that's why we have the math cal h on the right hand side.
I mean, that equation makes sense. The next one is I don't understand.
Which part?
3, 5, 3.
This. So that we get from just finding the holographic stress tensor in this. Yeah, you are process.
Yeah, but I understand the phi naught is will have the potential, but
smaller entity has to be satisfied in the CFT.
Oh, is this?
So you have
Is the H is the trace of the? No.
no. So it comes from like this. So you have the holographic stress tensor. Del T has to be equal to O del J.
Yes.
Now the O has to have these extra terms. Otherwise,
Yeah.
Okay. Yeah. So I was describing how we solve the dynamics of the system. So let's say at first iteration we just solve this scalar equation by putting this to right side to 0. So it's like a free scalar equation, but it's just the first iteration. So we solve this, get some initial guess for the chi by solving the equation, but we know the chi is proportional to phi naught, so we get the initial guess for phi naught. Now using this phi naught in the second step, we solve the gravitational system and we obtain the holographic operator H. Now with this new holographic operator H, we again solve this scalar equation by now putting this H obtained in the second step in the right side, and we get new solution for chi or equivalently phi naught. So then we just then again use this phi naught to solve gravity side and get again new guess for capital H. So that is the iterative process. We continue this till iterations converge. Iterations usually converges in 3 or 4 iterations. So one of the non-trivial thing is that we have this higher derivative terms in H, and so the initial conditions are the initial bulk profile of this bulk scalar, then initial mass of the black hole, and chi dot for the scalar, because if we did not have this H on the right hand side, this is a second order differential equation in T, so it will just need chi dot. But now there is this H on the right side and it involves the third derivative of phi naught equivalently chi. So, but still we don't need to specify chi double dot initial time, even though it involves the third derivative. Still the procedure always converges. So it is a non-trivial thing. Huh?
Beta is considered the small parameter here. You solve in beta is small parameter.
Yeah, it's usually small. Yeah. But we can also solve it for the larger beta.
If beta was not small, then the iteration, because the equation would be a third order.
Then?
The equation, if you put back the equation that you had for H,
Huh?
because chi is related to phi naught, then
Right.
you get if beta is not small, then it's one equation to solve.
Right.
Not solve directly.
Yeah, you mean this equation, right?
Yeah.
S-
Because you start to say you just solve first for chi,
Hmm.
the right hand side 0,
Yeah.
and then you iterate.
Mhm.
But if beta is not
It's a
small,
power series in beta.
it's
That's
not,
what-
yes.
It's a power series in beta.
Yeah,
That's
but
all.
typically it converges very fast, even in beta. Because beta is dimension 2, you have to see the correct thing is beta TQ or something. Even that is large, it's still converges. It's not like you converge a little bit more iteration, but not too many more iterations. You take more, yeah, you're right. I mean, you have to take more iterations to make it converge, but it's still a convergence for any arbitrary value.
Why can't it be asymptotic? How do you know it's not asymptotic?
Yeah, exactly.
But this is of course because you can only solve it numerically, you don't have an idea, but at least for beta TQ order 1, you can still find convergence. This is surprising actually. I mean, you don't need like 10 iterations, but that 8 or more iterations are needed.
3, 4, usually it's 3, 4 iterations. Even for beta, I think 1, up to 1. Large beta, there is numerical problem, so we don't know whether it is an analytical problem or numerical.
Because the beta can have a bound. It's possible that this breakdown, but we don't know it numerically. So our suspicion is that this is actually for many cases where we can work out linear fluctuation as Sukrut also has seen, when you take the limit beta goes to infinity, you get an emergent conformal symmetry in the whole system. It becomes another conformal. And that is well studied. So when you study linearized perturbations, we can take beta to be arbitrary in our analytical case.
Okay, so let me just show some of the plots here. So the left side, this plot is the energy of this perturbative sector chi, and right is the energy of the holographic sector. So this is different lines for different values of beta here. So usually what happens is initially some of the energy from the black hole is sucked by this perturbative sector, and at late times all the energy in the system always goes to the black hole. So the system always thermalizes. Okay, so here I just described so far the basics of semi-holography. Now I will focus on the thermalization in these kind of models. So let me first talk about the thermodynamic with how this model is consistent with the usual thermodynamics and statistical mechanics. So in equilibrium, this effective matrix that I talked about earlier, so G mu and G mu tilde, they can be parameterized in this way, where A and B and A tilde, B tilde are just some constants. Then there will be some two equations of states for two subsystems. Then you can write the stress. So this is, I am focusing on just 2 plus 1 dimension here. So we can write the stress tensors of the subsectors in this way, and these coupling equations become just the 4 equations in A, B, A tilde, B tilde. The full stress tensor, in the beginning I described, we can always construct a conserved full stress tensor, which will have this, again, the equilibrium form, where this math cal E and math cal P can be completely determined from the quantities of the subsectors in this way. Now we want to define the temperature for the full system. So what you would like to have is, so in equilibrium we would like to have just one temperature for the two system, but generally what we have is the temperature for the one system. We could define temperature for one, we could define temperature for other. So how would we have just one parameterization for the temperature of full system? So the full system temperature is math cal T, we define this way, the length of the thermal circle, where tau is the imaginary time, and so here there is square root of minus GB, because the GB is the actual background metric, and we, sorry, it should have been GB00, the time component, TT component, and we take here just the Minkowski, flat Minkowski metric, so this is just 1. Then with these effective metrics that I just showed, we can do the similar thing for T1 and T2, then we get these expressions. So we get here A for this and A tilde for that, and if you compare the 3 expression, we get this relation, where the T1 and T2 are always related to this temperature of full system. So this math cal T characterizes the equilibrium of the full system. Now next we want to define the entropy in this system. So we just take the intuition for usual stat mech. So if we have a microcanonical ensemble, an isolated bipartite system, let's say, then the total number of microstates are the product of the microstates of the first system times the microstate of the second system, number of microstates, and since entropy is the log of number of microstates, the entropy is always additive. Now here what we have is both the sectors are isolated with respect to their own effective metric backgrounds. So we would expect something similar, that the full entropy should be additive, maybe up to some factor, because they are isolated with respect to their own effective metric backgrounds. So let's find out. So we define, this del mu, S1 mu is the entropy current for the first subsystem. Now since first subsystem is isolated with respect to its own effective metric background, so according to second law, this will always be non-decreasing. So where del mu is the covariant derivative with respect to its effective metric. Similarly, the divergence of the S2 mu will be non-decreasing in its own effective metric. Then if let's consider this term del mu S1 mu, which we can write like this. Then we just multiply and divide by this term, square root of minus GB. If we do that, then we can convert this in terms of the covariant derivative with respect to this background metric of this term. Similarly for del mu tilde S2 mu. Then if we just if we construct this full entropy current, this math cal S mu as this, then these two expressions and these two expressions guarantee that this will always be non-decreasing. So what we have done is we have constructed a entropy current for the full sector, which is always non-decreasing. Then next we want to define the entropy. So this S1 mu, this entropy current of first system, we can write as S1 times u mu, where u mu is the 4 velocity. Now at equilibrium, this u mu is given by this 1 over a 0 0, and the square root of minus g and square root of minus gb will be these for this equilibrium parameterization, and Minkowski metric as the background metric. And then this S mu, we can see that the time component of it will give this entropy as S1 b square plus S2 b tilde square. So indeed we have the total entropy is the sum of the subsector entropies up to these volume factors. They appear because of these effective metric couplings. Now so far I defined the temperature and entropy in one particular way. So there is another way to define the same quantities, the temperature of entropy of the full system. So as I showed you earlier, we can always get the energy and pressure of the full system from the subsystem quantities. I showed some expression for that. So then we can use these two thermodynamic identities, and we solve them for these two variables T and S, and we should get the some expression for T and S. It turns out that whatever expression we get, that exactly matches with the whatever T and S that we defined earlier. So this is a way to check that our model is consistent with the thermodynamics and statistical mechanics, and this has been shown for arbitrary democratic couplings, this consistency in this paper. Maybe I'll skip this. So yeah, so like in usual StatMech, if we have a bipartite, if we have two systems in two different temperatures, and if we put them in contact with each other, then two systems will thermalize only when the entropy of the system is maximized. Now here our two systems are, although they are isolated with respect to, so we have two systems with T1 and T2, and they are conserved in their respective they are isolated with respect to their effective metric backgrounds, and then talk with each other in a very funny way. So that the idea that the system will thermalize when the entropy is maximized may not necessarily go over in this model, may not obviously go over. So an example is, it is possible, so we have two different entropy currents which are non-decreasing, so del mu S1 mu, del 2 S2 mu. So it is possible that dynamics can take the system such that one system ends up in some T1, other system ends up in T2, which are not necessarily related by this global equilibrium relation. In that case, we cannot define the temperature of the full system. So we call such configurations as pseudo equilibrium configurations. Even in these configurations, the entropy production will cease and system will be in some kind of equilibrium. So we call that pseudo equilibrium. Now, in case of the massless scalar for the black hole that I showed you, so there is no entropy current for this massless scalar. There is only one entropy current in this case. So that's why the system always thermalized, all the energy always went to black hole. But let's say if we have an MIS or kinetic theory and a black hole coupled to each other, in this case each of this system has entropy currents which are non-decreasing, and in that case we end up in these pseudo equilibriums. We have also seen this numerically. So then the question is, can the system thermalize if this is what we are observing? So the answer is yes. So, and let me describe how. So I will give a general proof for this first. So let's say we work in 2 plus 1 dimensions, and we have some arbitrary equations of state, P of epsilon, P tilde of epsilon. Now we fix the total energy always. So we are always working in the microcanonical ensemble. So the constraint that the total energy is constant will relate the two temperatures T1 and T2. Then the space of equilibrium solution will be parameterized by one parameter, because T1 or T2 related by this total energy constant constraint. So let's say the parameter is lambda. Okay, so now we have these 6 equations. So first equation is the derivative of the total energy with lambda is 0. Second equation is that the derivative of the total entropy with lambda equal to 0, because what we want to see is that whether maximizing the total entropy will imply the global equilibrium. And I showed you the 4 coupling equations in terms of these 4 metric variables A, B, A tilde, B tilde. So we just take the derivative of each of them with respect to this lambda. So there will be 4 more equations. So we have 6 equations here, in terms of these 6 variables which are written in this V vector. So a derivative of T1, T2 and the 4 metric things A, B, A tilde, B tilde with respect to lambda. Since all of these equations are linear in these variables, we can write this as a metric equation Q dot V equal to 0, where V is this vector. Now this has a non-trivial solution only if determinant of Q vanishes, and we have shown that determinant of Q equal to 0 implies this global equilibrium condition. AT1 is A tilde T2, which is the full temperature in thermodynamics. So what we have shown is that in microcanonical ensemble, if we maximize the total entropy, then we always end up in the global equilibrium. So, let me illustrate this with some numerical example. So here we have considered the 2 conformal systems. So there are 2 conformal equations of state. The left plot is the plot of the total entropy. The red line is the total entropy, and the blue line is the T1A minus T2A tilde. So at this point where we have this crossing, here this T1A minus T2A tilde goes to 0, and at the same point this entropy maximizes. The right plot is the total entropy red and the subsystem entropies orange and green. So there is a puzzle here, because let's say we start with some point on this red curve, say here, and we want to climb up the hill in order to reach the global equilibrium. There is an issue because always at any point one of the subsystem entropy decreases where other increases, and recall that we have 2 non-decreasing entropy current for 2 subsectors. So it cannot be that dynamic can decrease the entropy of any of the subsector. So how would we climb up the hill if we start at some point on this curve? So the solution is that we start at some point here, we add the perturbation. Now the non-equilibrium perturbation will drive the system out of this phase diagram, and that will decrease the entropy of the one of the subsystem, say this orange one, and then the dynamics will again obviously bring it back to another pseudo equilibrium, and the dynamics obviously will increase the entropy. But the initial decrease, if that is greater than the increase due to the dynamics, then there will always be an overall decrease in the entropy, and then we can end up in, then it is possible that we climb up this hill.
Yeah, but the point is that only when you are not exactly at the top but somewhere elsewhere,
Yeah.
there exist non-equilibrium perturbations that increase the total entropy,
Yeah.
but decreases the entropy of one subsector.
Yeah. Yeah, I was coming to that. Yeah, so let me elaborate on this argument by talking about these fluctuations. So I just consider one particular system to talk about this. So we have this 2 MIS things coupled to each other. We need that in order to add the fluctuations. So just 2 MIS things coupled. Let me show the plots. So this left plot is the plot of the fluctuation in the total entropy. So but delta S is the, so if you add the perturbation on the pseudo equilibrium, the entropy after adding the perturbation minus the entropy. I have? Okay. Okay, so delta S is the difference between the entropy after adding the perturbation minus entropy before adding the perturbation. Now we have plotted this as a function of number of perturbations. So what we have done is we started with some pseudo equilibrium, we add the perturbation, then system will relax to another pseudo equilibrium. We again add a perturbation, it relaxes to another pseudo equilibrium. We see this by adding the repeated perturbation where the system can go to global equilibrium. So what this plot tells us is that this delta S is positive, and at some point it becomes negative, and this is the point exactly where the global equilibrium happens. So this is somewhere 33 something. So this is the plot of this full entropy. So this global equilibrium is achieved at this point. Then the question is, why does system go even further? Like system should stay in the global equilibrium, right? But this can be argued in this way. So this delta S becomes negative exactly at the global equilibrium, and we know that, for example, this is the microcanonical ensemble where total energy is constant. The probability of particular configuration is given by the number of microstates. Now, the delta S is basically proportional to number of microstates. Sorry, the exponential of delta S is proportional to number of microstates. So exponential delta S is the probability of a particular configuration. So basically what this tells us is that all the configurations that we get after perturbing the global equilibrium are highly suppressed, exponentially suppressed, because here delta S is negative. So once we reach the global equilibrium, it's very unlikely that we will move away from the equilibrium. Now coming back to this S1 argument, the puzzle that I said that since one in this equilibrium plot, always one of the S1 was decreasing. So I explained, like, after adding the fluctuations, it is possible to go to decrease one of the S1. So this is because so one of the S1 so this is delta S1 and delta S2 for two subsystems. So one of them is always positive, other one is always negative. So this delta S2, so delta S2 is the difference so S2 after adding the perturbation minus the S2 on top of the pseudo equilibrium for which the perturbation was added. So what this tells us that after adding perturbation, delta S2 is always decreasing. Now after that, the dynamics that will relax it to another pseudo equilibrium, that will increase delta S2, but there will always be an overall decrease, so that there is no inconsistency to climbing up the hill. Okay, so let me just go to the final part, where we argue this kind of make these arguments when both the systems are now quantized. So this is still some work in progress, so the arguments here will be a little bit hand wavy. So here again we'll focus on one particular model. So this is some scalar coupling. So this is the action of the full system, which is S1 is the one of the sector, S2 another sector, and you have this term where alpha is this semi-holographic coupling. Now here both the systems are quantum, so they will be described by some density matrices. So rho 1 2 would be some density matrix of the full system, which generically will be some entangled density matrix. Now the coupling works in this way, that this J1 will be a function of the expectation of the operator of the second sector, so O2. Similarly, J2 will be a function of the expectation of operator of the first sector, and alpha would be the semi-holographic coupling. Okay, so we know that we can take rho 1 we can obtain rho 1 by taking partial trace of the full density matrix, similar over the second system, similarly rho 2 by taking the partial trace of the full density matrix of the first system, and the expectation of O1 will be just trace of rho 1 O1, and similarly expectation of O2 is trace of rho 2 O2. Now we want to do the similar thing as in the classical case. We want to solve the system iteratively. So how would we do this? So the time evolution would be done in this way, where we have U1 and U2, some unitary operators. They will evolve this rho 1 2 in this way, the usual way. However, U1 is not only doesn't only contain the things from the one sector, but it has, because U1 is a function of J1, and J1 depends on the expectation of O2. So, and similarly J2 depends on expectation of O1. Even though there is a direct product structure, the two things will get mixed up by these couplings. Now, so let me describe the iterative procedure in this case. So first we start with some arbitrary entangled rho 1 2. Then in first step we just set J1 equal to J2 equal to 0 to start the iterations. We obtain some expectation of O1 O2 by just taking the partial traces. Then this time evolution that I said will describe the time evolution of rho 1 2. So at first iteration we just have U1 of J0, U2 of J0. Now this will give us some new solution for rho 1 2. Now with this we again obtain the O1 and O2, the expectations of O1 and O2. And now then we again evolve rho 1 2, but this time there will also be these terms, J0 plus alpha O2 because that is what J1 is. Similarly, J2 is J0 plus alpha O1. And we continue this process till the iterations converge. Now, the one difference between the quantum case and classical case is that there won't be any pseudo equilibrium configurations in quantum case. So an entangled state, so a rho 1 2, a typical rho 1 2 will always be an entangled state, and it is unlikely to be stuck in some pseudo equilibrium. Why? Because we know that the unitary evolution will always increase the entropy according to second law, since our system is isolated. So it will always increase the entropy of both the rho 1 and rho 2. So if rho 1 is thermal, then it has a maximum entropy, and it will always be invariant under the time evolution. Yeah, coarse gradient. Yeah, and so as we saw in the earlier numerical study that there are many non-equilibrium configurations which have more entropy compared to a particular pseudo-equilibrium configuration. Therefore, when we take the trace, partial trace of rho 1 2 to get these rho 1s and rho 2, it is much more likely to end up rho 1 as a non-equilibrium state than some pseudo-equilibrium state, simply because the non-equilibrium state will have much more entropy than a pseudo-equilibrium one. And once both rho 1 and rho 2 reach the thermal equilibrium, they will always stay there because a thermal state is invariant under unitary dynamics. So we want to study this example in the, so we want to actually implement this iterative method and see exactly what happens. So for example, in the case that I described earlier, where a boundary scalar was coupled to a black hole, so we will quantize the boundary scalar and the bulk scalar field, and then we can implement this method and see what actually happens. Also, in tomorrow's talk by Tanay and Hareram, they will describe a system where you already have a boundary system quantized, but not yet the bulk system quantized. Yeah, I think that's it. Thank you.
So it's open for questions or comments also.
For the iterative solution we discussed earlier, do you have the first few terms analytically, or did you only have a numerical solution?
Yeah, we only have numerical solutions.
So you do not really know what it is.
Yeah, we don't have any analytical control to find it out.
For this two-fluid model, is there a top-down construction of that thing? Is there a top-down construction of that kind of coupling?
To mean whether we start with some black hole or something
Not
and get
black hole, some gauge theory system, or I don't know, some microscopic system, and you get those couplings.
Mm.
Kind of put in by hand. Yeah, this is what I was.
So
Yeah.
I don't think there is a I mean, deriving it will be hard, because usually in string theory you only have the fully strongly coupled sector, and then you also already, or like n is equal to 4 or a weak coupling description. To have something in between where you have both closed strings and open strings together, and is of course a much harder thing. But here you are simply guided by some consistency and try to see where you can go. So the idea is as follows, that the non-perturbative sector and together with the perturbative sector, you will get a well-defined Strand series. For example, when you do OPs, you get this OPE coefficients which have some kind of perturbative expansion, but that perturbative expansion has renormalance, and that is cured only when you take expectation value of operators in some states, and that cures the renormalance. That has been observed by Parikh. But these expectation values of operators, they can be generated by some holographic geometry which has the right kind of designer gravity kind of approach. So that's the idea that that you could do. So you should be guided here by completely some kind of consistency conditions like that, because we don't have a description of string theory in these limits where you have, for example, n is equal to 4, either weak coupling or strong coupling, right? Yeah. So you don't have a full, very well controlled description of string theory in between. So this is the problem that there's a top-down derivation is hard.
Any other questions? If not, let's thank Sukrut.
Am I audible? No. Am I audible now? Little bit. Okay.
So let me just.
Yeah. Okay. Yeah.
So our next speaker will be Shanmugapriya. She's going to talk about black hole hair removal, and she's changing the slide that I'm reading the title, and positivity of microstate degeneracy.
Okay. Yeah. Good afternoon, everyone. It's a pleasure to be a part of this conference. So let me start by thanking the organizers for inviting me to present our work. My talk is titled Black Hole Hair Removal and Positivity of Microstate Degeneracy. It is based on the following two papers, and my talk is divided into two parts. The first part is going to be about black hole hair removal for n equal to 4 CHL models. And this is some work that we did with Subranil Chakraborty, Suresh, who's right here, Yogesh, and my advisor Amitabh. The second part of the talk is about positivity of discrete information for CHL black holes. Again, this is some work with Suresh, Sutapa Samanta, and Amitabh. So let me give a brief outline of the talk first. So I will start with the puzzle at hand and briefly review the model of interest. Following that, we will construct black hole hair candidates for the 5D and 4D black holes. What these two black holes are, we will see shortly. After having constructed the hair candidates, we will see how many of them actually correspond to black hole hair modes. With the hair modes in hand, it will lead us to the resolution of the puzzle, which is going to be by hair removal. And this will mark the end of the first part of my talk. After this, I will talk about positivity of microstate degeneracy, where we have computed a wide class of microscopic indices, and we get some interesting information out of them, and we will see what that is. I will then finish with a summary and some future directions. Okay. So how do we define black hole hair, and how is it that we even have them in our model? Because we know that John Wheeler famously made this statement that black holes have no hair. So basically they are bald objects. And this is what we now know as the no hair theorem, which states that in the absence of any other matter content except a Maxwell's field, a black hole is completely described by its mass, electric and magnetic charge, and spin. However, for more complicated setups like higher dimensional theories, presence of form fields and fermions in our theory, black hole hair is indeed possible. In their 2009 paper titled Black Hole Hair Removal, Nonlinear Analysis, Jatkar, Sen and Srivastava define black hole hair as smooth, normalizable, bosonic and fermionic degrees of freedom that live entirely outside the horizon. And it is this definition of black hole hair that we will also adopt in our context. Now, having a sense of what we mean by black hole hair, we will see why we are looking for them and why we need their removal. Computations of black hole entropy in terms of microscopic degrees of freedom are known to be insensitive to the nature of the solution away from the horizon. So this means that if we have two different black holes with identical near horizon geometries, they should have the same microscopic indices. However, an apparent counterexample of the same was found in the case of a BMPV black hole in flat space and a BMPV black hole in top-notch space. So although these two black holes have identical near horizon geometries, a mismatch of indices was found in this case. So Banerjee, Mandal and Sen in their 2009 paper, Banerjee is of course Nabamita who is right here, they proposed black hole hair removal as a resolution for the above conundrum. So once we remove the contributions to the partition functions from the black hole hair degrees of freedom, we are able to see perfect matching of indices. Again in 2009, Jatkar, Sen and Srivastava explicitly computed these hair modes. Motivated by this, we would like to see if we can construct hair modes, and we would like to see whether black hole hair removal is the resolution to a similar puzzle in the case of general CHL models. So what is our model of interest? Exact computations of microscopic indices with n equal to 4 supersymmetry has seen enormous progress over the years. There are several papers on this topic, and for such discussions, CHL models provide a very rich arena to play with. CHL, which stands for Choudhury-Hockney-Licken models, are obtained as Zm orbifolds of type 2b theory compactified on K3 times S1 times S1 tilde. And the black holes of interest in the CHL models can be thought of as black holes in 6-dimensional 2,0 supergravity, which is coupled to nt number of tensor multiplets. So what is the field content of this 6-dimensional 2,0 supergravity coupled to nt tensor multiplets? On the bosonic side, we have a metric. Sorry, 6-dimensional. So we are looking at 2,0 coupled to nt1 in 6 dimensions. That is also a consistent truncation for this case. So on the bosonic side, we have a metric, self-dual and anti-self-dual two-form fields and several scalars. The fermionic sector contains gravitinos and other Majorana fermions. And the solutions that we will consider are such that all the scalars are set to constant and all the spin half and anti-self-dual two-form fields are set to 0. Furthermore, our solutions are such that they preserve 4 out of 16 supersymmetries. So basically they are quarter BPS solutions. Sorry, one second, I think, yeah. Okay, so let's briefly look at the black hole metric. For simplicity here, I have shown the case of a non-rotating BMPV black hole metric, although all of the analysis that we have done in our paper has been for the rotating case. So the BMPV black hole in flat space, which is going to be called the phi d black hole from now on, is given by the following metric. So we have the coordinates u and v given by x phi minus t and x phi plus t, and these wi's are the 4 transverse Cartesian coordinates. The BMPV black hole in the top-notch space is obtained by replacing this 4D flat space part by this top-notch metric. And here psi of r and chi of r are just 2 functions of r, where r0 and r4 are some constants. So the details of this metric is not very important, but what we should remember is that it can be shown that these 2 black holes have identical near horizon geometry, and the horizon is the r equal to 0 surface. So it's easy to see that once we take an r going to 0 limit here, the top-notch metric essentially reduces to the flat space metric. And one more thing that will be useful to remember is that this metric is independent of the u coordinate, and this is something that we will come to later. Okay, so what is our aim? Our aim is to construct black hole hair and to see what kinds of hair we have and how many of each kind we have. However, analyzing all possible hair is hard, because if we have a few hair modes in hand, there is no proof that these are the only hair that exist. And furthermore, even if all the hair candidates are not known, sufficient matching of the indices can be explained by just the knowledge of a few hair. So this means that there could be other hair which are equal in number and of the same kind for both the black holes. So basically they will give rise to the same kind of terms in both sides of our equation, and their presence or absence does not matter for our purposes. So this is what we will do. For these two black holes, we will only study these three hair, which are Garfinkel-Vachaspati, form field and fermion hair. And then we will try to see if matching is possible with just these hair. If yes, then we have achieved our purpose. Okay, so now let's go ahead and construct black hole hair candidates, starting with the 5D black hole. Okay. On the bosonic side, we will start with the Garfinkel-Vachaspati transform. This is a solution generating technique that adds wave-like deformations on a metric. So we take a known solution, apply the Garfinkel-Vachaspati transform, and we will get new exact solutions to our equations of motion. Of course, this transform cannot be applied on all metrics. Our known metric should contain a vector field Km, where M is the space-time coordinate index, which is null, hypersurface orthogonal and killing. And the matter fields which, if any, present in our theory should satisfy certain mild conditions. But basically the matter fields do not transform under the Garfinkel-Vachaspati transformations. So our GV transform gives us a new solution G prime from an old solution G by adding a deformation T. So the equation is here, and in this equation the scalars A and T are such that T satisfies the wave equation, and it also satisfies another constraint which just means that T is independent of the killing coordinate. Now does our black hole metric contain the vector field that we seek? Indeed it does. So we do have the vector field, the killing vector dou by dou u, and it can be shown to be hypersurface orthogonal with the scalar A satisfying the relation that e to the A is psi of r. We find that our deformation T is independent of the u coordinate. So this means that our new solution G prime also possesses the same null killing vector field, and the V dependence of this deformation T is unconstrained. For the BMPV metric, the Garfinkel-Vachaspati transform adds a deformation only to the GVV component of the metric, and this deformation is of this form. So again here the W's are the four transverse Cartesian coordinates, and upon solving the equations we get our deformation T as Fi of V times omega I or Wi, and here we see that these Fi of V are four arbitrary scalar functions of the periodic coordinate V, and it is these four scalar functions which will be our bosonic hair candidates for the 5D black hole using the Garfinkel-Vachaspati transform. We can obtain the fermionic hair candidates by solving the fermionic sector equations and obtaining some deformation psi alpha m. Alpha here is a spinor index.
So why does it satisfy the criteria that you just said? Or that you have support only outside?
These hair, oh no, these are just hair candidates. So I haven't actually told you whether these are hair modes or not, and we will see later that actually for the 5D black hole these Garfinkel-Vachaspati are not hair modes. So I will explain that in the later slides. Okay, so once we solve the fermionic sector equations, we obtain two possible solutions. So we get psi alpha V1 or psi alpha V2, and we find that each of these solutions have four independent components. So our fermionic hair candidates for the 5D black hole are going to be either these four or those four. And further, these psi alpha V actually remain valid solutions to the fermionic equations even in the presence of the Garfinkel-Vachaspati deformations that we constructed before. So even with G prime, these are valid solutions. So these are actually the fully non-reacted solutions, fully non-reacted, back-reacted theory, non-linear theory. Okay, now let's go ahead and construct Hare candidates for the 4D black hole. Again, on the bosonic side, we will start with the Garfinkel-Vachaspati modes. So here, we will again identify our null killing vector, and we will add a U independent deformation, which is going to be called T tilde now, again only to the GVV component of the metric, and it takes this following form. Here, in solving for T tilde, we can choose T tilde to be independent of the x4 coordinate, and what we get is a wave equation in the 3D transverse space, which is by yi, and the solution is of this form gi of v times yi, and we see that there are 3 arbitrary scalar functions gi of the periodic coordinate v in this case. So for the case of the 4D black hole, using Garfinkel-Vachaspati modes, we have 3 Hare candidates. But this is not all on the bosonic side. Yeah, pointed there. Yeah, it's just okay. So this is not all on the bosonic side. So far, we have constructed Hare candidates only in the 2,0 sector of our theory. We have the tensor multiplet sector, where now we will try to construct some NT number of deformations. The top knot space is equipped with a self-dual harmonic 2-form field omega Tn, and using this 2-form, an anti-self-dual 3-form field delta Hs Mn can be constructed like this. So initially, when we looked at our solutions, we have set all our anti-self-dual form fields to 0. Now these can be thought of as some deformations on top of those vacuum solutions. And each tensor multiplet had one anti-self-dual 3-form field, and therefore for NT such multiplets, we have NT number of these deformations. Now these anti-self-dual 3-form field deformations will go into the bosonic sector equations, and they will cause some collateral damage. So this calls for a corresponding set of deformations in our metric. And here again we get some deformations in the GVV component of the metric, and these are denoted by S tilde, and these S tilde turn out to be quadratic in the scalars Hs of v that we saw here. So the point to remember is that these two deformations are actually not independent of each other, because one arises as a result of another, and so the number of form field deformations that we have for the bosonic side using this 2,0 sector is only going to be NT number of arbitrary scalar functions Hs of v.
Again, this also modifies in the GVV.
Yes, also modifies in the GVV. Sorry, yeah. So the story is not very different for the 4D black hole on the fermionic side. Again, we must find a deformation psi alpha x by solving the same set of equations in the top knot background now. And again, the same candidates arise for the fermion Hare, which are the same psi alpha v1 and psi alpha v2. So the top knot space actually does not have any effect on our fermionic deformations, and the independent arbitrary functions of v here are going to be 4 each for psi alpha v1 and psi alpha v2, and these are our candidate fermion Hare for the 4D black hole. Okay, so now our job is done. We have constructed all the deformations that we wanted to construct, but so far we only refer to them as Hare candidates. We have to now find out how many of them actually correspond to Hare modes, how many of them conform to the definition of a black hole Hare that we gave in our very first slide. So we return to the eternal question that has been haunting us since the time of Shakespeare. So in order to determine whether a mode is a Hare or not, we need to perform 3 checks on all our deformations. So we need to perform a smoothness check. We ask, are the deformations smooth near the horizon? So in order to do this, find this out, we define suitable smooth coordinates across the horizon, and we perform a smoothness check on each of our modes. Secondly, no additional supersymmetry should be broken by the deformations. So we ask, is filling spinner analysis affected by our deformed solutions. And finally, each of our smooth deformations should only be supported outside the horizon. So does our hair live only outside the horizon? Upon doing these checks, we find our culprits. We see that for the 5D black hole, the 4 Garfinkel Vachaspati modes are not hair, but the fermion modes, there are 4 of them which turn out to be black hole hair modes. In the 4D side, we see that all 3 deformations actually give us black hole hair modes. So what is happening here? Okay, let's look at the 5D black hole first. We find that all of these hair mode candidates are supported outside the horizon. But then the Garfinkel Vachaspati modes, that is the 4 functions Fi or V that we computed, they blow up at the horizon and they are not smooth, so they should not be counted as black hole hair. Among the fermion modes, we see that only psi alpha V1 turn out to be hair modes, whereas psi alpha V2 is neither smooth at the horizon nor does it preserve SUSI, and so it is not a hair mode. So overall, for the 5D black hole, we have 4 fermionic hair. Now let's look at the 4D black hole. Again, sorry. No, we have all of this is like the fully back reacted solutions. Yes. So the fermion, they will not give rise to any contributions to the metric equations. Fermionic equations, they don't give any contributions. We can. So the analysis is done in by. So we have all of these tensor equations, and we split them into equations which have different weights. So the weight of equation is defined as the number of V indices minus the number of U indices. And what happens is these different weight equations, they don't talk to each other. So when we have these fermion deformations, they are a psi alpha V, so that's a weight 1. And in our bosonic sector equations, they will not contribute. That is weight 2. Sorry?
I would thought the fermions, there is an energy momentum tension would be on the right side.
How is it for the?
An energy momentum.
Yes. Yes.
Would be on the right side. Einstein equation.
I think they don't contribute.
Like maintaining weight 2 is having the right derivatives.
Yeah. With the weight argument, one can show that it is, these will not go into those equations, that they don't actually interact.
So they have 0 elements. This specific solutions in 0 elements.
The fermion modes support outside the horizon, but PVV is 0.
They have 0 energy simply, I mean, because they're not messing up BTS.
Okay, yeah, I guess that's. So they are non-trivial and still have 0 elements.
Yeah.
So this is all at the horizon. Outside.
Outside the
Outside the horizon. They vanish at the horizon.
Hair modes vanish at the horizon, they are only outside the horizon.
So there is a non-trivial profile, but somehow it has 0 elements. It sounds a little magic.
Maybe not
Not,
PVV component is 0. They don't back react on the metric. But if one
If the
does
other components were 0, then still back here.
maybe if one does the ADM mass, the fermions may contribute to that. Not sure.
Little mess up BTS.
It looks quite counterintuitive. They have non-trivial excitation and 0 element and non-zero.
Yeah, that's sort of exception.
I mean, of course, yeah, but it's still.
Okay, so for the 4D black hole, again we see that all the hair modes are supported only outside the horizon. And the Garfinkel-Vachaspati modes in this case, the 3 scalar functions gi of v, they in fact turn out to be hair modes. And again in the fermion modes, we have only psi alpha v1, 4 modes. Psi alpha v2 is again discarded. And here in the 4D black hole, we also have nt number of form field deformations, which are these scalar functions h of v. And these are also our hair modes. So overall, for the 4D black hole, we actually have nt plus 3 bosonic hair and as well as 4 fermionic hair.
So they don't have mass. They contain momentum. In the
Yeah. So, no, there is a mass because you're right. They carry charge.
in the v direction
They
they have
carry
momentum. So to compensate for that momentum, they do carry mass.
This is the only modification to the solution to the contribution to the mass. And the charge, yes.
I'll carry on. Okay. Okay, so what have we done so far? We have explicitly constructed black hole hair modes for the 4D and the 5D black holes. And this is a spectrum that we observe. For the 5D black hole, there is no bosonic hair and we have 4 fermionic hair. For the 4D black hole, we have nt plus 3 bosonic hair and 4 fermionic hair. So all that one needs to remember in whatever has been done so far is that the 4D black hole has nt plus 3 additional bosonic hair modes than the 5D black hole. And this will be something that is important when we come to the hair removal discussion. Okay, so now with our hair modes in hand, let's go ahead and remove them from our partition function. Okay, so here is a figure of a BMPV black hole in flat space, and on the right we have a BMPV black hole in the Taub-Nut space, and this is just a pictorial representation to show that these wavy blue lines here correspond to our additional nt plus 3 hair modes that we observe in the 4D black hole. And what exactly do we mean by black hole hair removal? We just take the partition function of the 4D black hole and mod it out by this hair partition function. And the expectation is that it should match with the partition function of the 5D black hole. And with hair modes, if we do it, then we have solved our puzzle. It's also known that
It can be done on both sides if you have.
yes. Actually, but I mean, as you'll see, on the 4D side we have nt plus 3 and 4 fermionic. Here also we have the same 4 fermionic. So those contributions cancel and we can just yes.
But I'm saying that in case there are
Hair, yes, on both sides.
So
Yes,
you are basically not going to take their contributions to the partition.
to the partition function, yes. Okay, so it is also known that the 4D partition function is given by an inverse of this function phi tilde, which is what is called a Siegel modular form. It's a function of 3 complex variables and it has certain interesting modular properties. And this we will come to in the second part of our talk when we talk about positivity of microstate degeneracy. Okay, so what is our question? Do the hair modes that we have just constructed correctly account for the mismatch factors between the partition functions for each orbifold Zm? In order to answer this, we note that Zm group action is going to be on the 19 anti-Sirtual form fields that arise from the RR4 form when we reduce from the 10D theory to the 6D theory. Orbifolding will generate twisted sector modes, each with a twist of e to the 2 pi I s over m, where s runs from 1 to m minus 1. The untwisted sector is denoted by the case where s is 0. It is the presence of these twisted sector modes that cause additional complications for our CHL models. So let's look at 2 examples and see how we are able to account for the extra factors by our hair modes. First, we will look at the Z2 orbifold, the case where m is 2, and here the split of the 19 form fields is into 11 in the untwisted sector and 8 of them with a twist of -1. And this reflects, actually these numbers 11 and 8 reflect here the exponents of these factors of the infinite series expansion, which comes in the partition functions. And by some algebra, we will be able to show that this reduces down to certain products of eta functions. For the Z2 orbifold case, it is precisely this f of rho, which is our Hare partition function, which is just a mismatch factor. Again, in the m equals 3 case, the Z3 orbifold case, 19 is split into 7 untwisted sector, 6 of them with a twist of omega, 6 of them with a twist of omega squared, where omega is the cube root of unity. And here again these numbers are reflected in these exponents and they can be neatly packaged into this product of eta functions. And for the Z3 orbifold, it is this f of rho which is the mismatch factor that we have. We have similar such computations for all the other orbifolds that we have seen in our paper. And in each of them, we are able to find that our f of rho correctly matches with the extra factors that we have, and hence it resolves the puzzle. Okay, so let me briefly summarize the first part of my talk. A mismatch of microscopic indices was observed between two black holes in the case of ZM-CHL orbifold models. For each such orbifold M, the additional Hare modes correctly account for the extra factors. Removal of these Hare modes has matched the 4D and 5D partition functions and it has solved the puzzle. Now, because we have obtained this matching, any other Hare that would be expected in the model would appear in equal numbers and it will be of the same type for both the black holes. But they don't matter for us. So this marks the end of the first part of my talk.
I'm sorry. So if more of them are there, then you would say that for individually for both the black holes, the partition function will be different. It would match.
Individually, the partition functions will be different, but because they are of the same kind,
No, I agree
yes.
that the puzzle that you are talking about.
Yes, that will be solved, but individually will be, yes.
But that you should be able to, I mean, since these partition functions will tell you about the entropy of the black hole.
Yes, we can get them from the, I think the quantum entropy function, that formalism deals with individual partition functions. We should be able to do it from there, yes. That is a difficult question. Nabamita actually.
How many symmetries are broken in what way? And then probably some other instinct from saying that I also don't know.
If one has a very deep insight into the construction of 4D and 5D partition function, then one can arrive at it.
No, mostly I think symmetry is breaking is what you say.
Yeah, but this using Garfinkel versus which is yours, right?
No. Second paper.
Second paper, Jatkar and
In that paper, they explicitly constructed
Yes.
them, but in our paper, we didn't construct them.
We just said-
We just found which one of them should be broken
Yes.
and then subtracted them. I mean, plugged them. I mean, this looks like, in fact, a much more like formal way of doing it, where one should be able to get.
No, but actually, one nice thing which Amitabh and Shanmugapriya have done in this problem to track. See, you don't have orbifolds in crystal centers, you do not have in gravity. So they went back to 10 dimensions and worked out how the fields transform under the action and then work backwards. That's actually a beautiful. The first time I'm seeing some supergravity where twisted sector is coming. Yeah.
Okay, so now let's move on to the second part of our talk, which is about positivity of microstate degeneracy. index versus degeneracy is a popular puzzle in the literature. Although when we do comparisons with the macroscopic entropy, we always deal with the degeneracy of the microstates. It is the index that enters the microscopic computations because it is the index which is protected under supersymmetry and hence it can be computed in the weak coupling limit. Further, Sen argued that for single-centered quarter BPS black holes in 4 dimensions, the negative of the index is nothing but the degeneracy of the horizon states. Now, since degeneracy is an innately positive quantity, this means that our index should be negative. So, how do we get these indices? Certain Siegel modular forms which are associated with appropriate partition functions are known to us. And the index is precisely the Fourier coefficients of these Siegel modular forms. So, using a mathematical program, we can just get all of these Fourier coefficients and we will have our relevant indices.
What was the argument for the index being degeneracy?
This one? I think it was when we have quarter BPS black hole, we look at a certain index, the helicity trace index B6, and in that index the contributions from the fermion zero modes, those will actually give rise to these minus factors, and so using that we can.
Why is the index giving you the degeneracy? Because it's a difference of things. So the true answer is that at least for half BPS, what happens is that what you get is the BPS condition is keeps everything on the ground state the other side, and the other side you will get in the heterotic picture you will get just a bosonic excitation. So it's the dual picture is very clear. Is that truly just only bosonic excitations. Okay. Index equal to.
Yeah.
But the same n equal to 4 here is with any type 2 models where it's not true. Index is not equal to the example.
Okay. So this index, the claim is that this index, the negative of this index should be a positive quantity. And it is this positivity of microstate degeneracy that Sen illustrated for the case of low charges in the ZM CHL orbifold models in his paper, How Do Black Holes Predict the Sign of Fourier Coefficients of Siegel Modular Forms. Now, a key assumption of this paper was that the bosonic and fermionic Hare modes that we constructed in the previous part of the talk do not exist in the frame in which these indices are being computed. So, the relevant index that we are looking for is this helicity trace index B6, which is given as this trace over a sum of states and trace over a set of states, and H here is the helicity of the states. Now, Sen in his 2010 paper gave the following table, which has the values of minus B6, and this is for the Z2 CHL orbifold model, and this is given for different values of black hole charge gamma p, and here it's only these whole phase entries that correspond to the index of the single centered quarter BPS black holes, and we see that all of those entries are positive as expected. In more recent news, Justin and Aradhita in a set of papers in 2017 and 18 observed that the positivity of minus index fails in the case of ZM orbifolds of toroidal compactifications. Yes, this is type 2 theory. Yes, type 2 on torus. Where it is, yes, it fails. I mean,
Yeah, no, that's true, but I think there is some point in Justin's and Aradhita's paper. They correspond to regular physical practice, and the argument that the index is minus the degeneracy, that argument still works.
No, I don't think so, because the analog is also like for half BPS kind of thing, right? So now there one side on ground state, the other guy will be now a type 2 thing, which they're both fermionic and bosonic. But I'm saying the CFT one is now like a supersymmetric
discussion. We are not worried about the toroidal compactifications actually.
No, but this is actually very interesting.
Okay, so they conjectured that the contribution from the hair modes could be destroying its positivity property. But we will not be interested in the toroidal compactifications. We are only interested in looking at the index of the horizon states they computed for the case of ZM CHL orbifolds, and these were studied in the 2020 paper. So basically this was done by isolating by hair removal again the horizon degrees of freedom from bosonic and fermionic hair modes and computing the index. And here is a table of the same index minus B6, but this is the hair removed index and this is for the Z2CHL orbifold model. And here again we only need to concentrate on the boldface entries which correspond to single centered quarter BPS black holes, and all of these are positive. Okay. Now unorbifolded models but with a discrete Zn symmetry was studied by Sen in 2010, and the action, this Zn symmetry was called twining symmetry, and its action on the black hole charges was to leave them invariant. Accordingly, he defined a twinned helicity trace index which is B6Gn that is given by a similar trace over states, but it also has a Gn insertion in it, and Gn is the generator of the Zn twining symmetry. Now using certain Siegel-Maurer forms that are different from the ones that we saw before, we can extract these twinned helicity trace indices also as Fourier coefficients in a Mathematica program. However, although up to now we have talked about positivity of index, these twinned helicity trace indices can in fact be negative. This is because they don't have an interpretation just as a number of states, but their interpretation is that of a weighted sum of states. So to understand this, we will look at an example. But before we go to the example, what is the significance of these twinned helicity trace indices? It is that they give us additional information about the distribution of these Zn charges among the black hole microstates. So it is in fact possible to compute the number of microstates, which is denoted by minus SA, which carry a definite eigenvalue under the Zn twining symmetry, and it is this minus SA that should be a positive quantity. Yet again in 2010, Sen and Suresh also has given us these Zm cross Zn models, which are basically involve both the CHL orbifold as well as the twining symmetry, and accordingly we can also look at certain twisted twinned indices, and twisting here is just another name for the CHL orbifold action, and so we can look at these twisted twinned indices for the Zm cross Zn models for various values of m and n. Okay, just a quick recap of all the indices that we have seen. So when we have a CHL orbifold, Zm orbifold, we are interested in the index minus B6. When we have twining alone, no orbifolding, we come across twinned helicity trace indices B6Gn, and when we have both CHL and twining, we have twisted twinned helicity trace indices. Now, what is our aim in the second paper? And here is where I will also show an example. We would like to compute the twisted twinned indices of Zm cross Zn models involving both the CHL orbifold and a twining symmetry, and we would like to investigate the positivity properties of the various SA indices that we get. Now let's look at our example. We will take the simplest case, which is of a Z2 cross Z2 model, and here under Z2 twining symmetry, our microstates are divided into two sets. So there are going to be S0 number of states which have an eigenvalue plus 1 under the twining action, and we have S1 states which have an eigenvalue minus 1 under the twining action. In terms of the indices that we saw before, S0 is just the sum of B6 and B6G2, and S1 is just the difference. Of course, there is a factor of half. So what we have done in our paper is we have obtained the values of minus S0 for the Z2 twine partition functions of the Z2 CHL model. Again, it's only the boldface entries which are important, and here we see that all of them are positive. We also have the values of minus S1 for the Z2 cross Z2 model. Again, boldface entries are all positive. Now we go back to this formula, and when we invert this, we see that B6 has an interpretation as just the total number of microstates. So B6 does not really care about what our Zn twining symmetry is doing. So this is something that, but this B6 table for the Z2 CHL model is something that we already saw. So let's just take like one entry. Supposing we look at this entry for this set of black hole charges. So minus S0 is 176 and minus S1 is 184. And this should coincide with the B6 value that in the table that Sen gave us. Point there, okay. Yeah, so sum was 176 plus 184, which is 360. And this is the table that we can actually reproduce from our minus S0 and minus S1 values. So we are going in the right direction. Okay. Now here we can also look at B6G2, which is going to be the difference of S0 and S1, and we find that B6G2 does not exhibit positivity. It is 176 minus 184. It does not actually exhibit positivity. And since this has an interpretation as just some weighted sum of states. We have similar such tables for other models with other values of M and N, and for all of those cases we are able to identify the different values of SA. Okay. So, okay. Now let me summarize the second part of my talk. What we have done is we have shown the positivity of the various indices SA for the case of twining symmetry alone, no orbifolding, and this has been verified for Zn twining n equals 2, 3 and 4. We have also shown the positivity of the various indices SA for the CHL twine models, so twisted twine models for the cases Z2 cross Z2, Z3 times Z3 and Z2 cross Z4. And here for the Z2 cross Z2 case, we are able to use some functions which Sen gave in his papers, but for Z3 cross Z3 and Z2 cross Z4, those computations are horrendous. So we haven't been able to do them using Sen's formulae, but Suresh has given us in his paper in 2010 some formulae with our products of some theta functions, and we also have what is called Borcherd's lift, and using we are able to obtain the indices for these two models. And we have also verified that for the Z2 cross Z2 case, at least we have verified that all the three representations actually agree. So we are in fact going in the right direction. And we find that all of these integers, all of these indices turn out to be positive integers. Now looking at the expressions for S0 and S1 in terms of B6, B6G2 and all the other indices SA, we can actually give predictions about the signs of certain linear combinations of Fourier coefficients of Siegel modular forms, because we actually derive all these indices from our Siegel modular forms. Okay, so what is the path forward? We can ask, what about T4 models? What about toroidal compactifications? There could be other hair to analyze and include in these cases. In fact, we also have with us a ready-to-use technique, which is a generalized Garfinkel-Wichaspati transform, and that is basically the generalization of the GV transformation that we saw here. And this was a technique that was developed in 2018 and 19 by Shubhranil, Deepti, Yogesh and Amitabh. The catch is that an additional vector field is needed, and in this case for generalized Garfinkel-Wichaspati, the matter fields also undergo a transformation. So currently in some work in progress with Subbu and Amitabh, looking at a version of the positivity puzzle for the toroidal compactifications. In the case of the CHL twine, that is in the case of the folded and twine models. So Justin's work had some, they were having a puzzle for the case of the T4 compactifications, no twining. We would like to see whether there is a similar puzzle when we include twining, and thus black hole hair removal come to our rescue again. So we hope to report on some of these problems in the future. So please stay tuned, and thank you for your attention.
It's open for questions.
Can I go back to the fermions? So usually fermions are intrinsically quantum. So if you want to back react with the fermions, you need to work out the expectation value of the energy momentum tensor. So this would mean that you would have to quantize the fermions in the black hole background and then work out, is this what you did or is this? But the Einstein equations have on the right-hand side the energy momentum tensor, but fermions they're not classical. They're not classical objects. You need expectation values of quantum operators.
That part we have not. I mean, we just looked at the weights of the various terms and we argued that the weights are such that.
Okay.
Any other questions? I have a comment. Dilip and I wrote for these type 2 examples, we have the Siegel-Mondler forms in a paper.
Yes. Twisted.
Not twisted twining, but I think I can cook up the answer for twining also. So, yeah. Are there any further questions? Okay, so when is our tea break?
We finished 20 minutes ahead of time.
Okay. So anyway, let's first thank Shanmugapriya. We can have discussions and yeah. So since we have 20 minutes, maybe if anybody has questions to ask all the speakers of the morning session, you can at this point. Or any speaker wants to give comments. Nobody. Yeah.
So why it is that you can choose only a unique vacuum indecitor somehow in your setup? I mean, there should be a way to.
We use the usual prescription of you choose boundary conditions and then you impose regularity in the interior, and that fixes the solution. If you want to choose a different state, then you have to do the real time. Then, of course, this would modify the equations in the real time prescription. Yeah, you go to minus infinity. That this selects the J. And then from the other solutions also, the solution was uniquely fixed after you imposed regularity. So you had to impose regularity when you cross the horizon. This was the most non-trivial step because, of course, the solutions are given a series and a mass. And it's a complicated expressions. And then you would see that the solution was non-analytic unless you specifically fixed them the way we gave them. So there was a unique solution to the regularity requirements. And of course, in the CITRA, there are all this alpha vacua and so on. There's no obvious sign of them. But again, I mean, it is an interesting question whether perhaps by putting a Euclidean cap, where in a sense it's not regular in a sense. You know, you're allowed to be singular, but in the part of the space-time, you kind of cut away and you put the cap in maybe some some construction of this type.
I have another related question. So we know that global ATS has some instability, but not of the linear kind, of a non-linear kind, for example.
Mm-hmm.
So because you are claiming somehow that you have resolved all these infrared puzzles in Desitter. So
Well, in that specific example, yes.
But okay, in that example, is it also prudent to check something whether this because you have what bothers me is this singularity, that there was a specific kind of singularity which has sort of like end of space time.
Yes, end of space time. Yes,
So
yes.
the question is that whether that can, if you at a non-linear level, it can give rise to some kind of instability. No, it simply states that the vacuum is original vacuum is not.
Yes, and I think I would agree with that. In a sense, once you perturb the theory, eventually, unless it's very, very special or the perturbation is fine-tuned, the system would thermalize. I think it's natural. The ADS instability is completely natural. Now, in this context, in a sense, we deform it in a very specific way, so it's just became. It's like the holographic RG flows are not unstable, right? They describe it is similar to the holographic RG flows what we did. So from that perspective, I wouldn't expect an instability. Of course, once you have that system, if you do the analog, you put some more, you excite again the system on top of that in a generic fashion, then the system would again.
Based on finite fields. So I think the classical codes, I don't know what requirements are there on classical codes, but once you have a classical code, you run it through CRSS, it becomes a code in a subspace defined over finite fields or extensions of finite fields. Yeah, so there is no direct connection to PRX, but these quantum stabilizer codes are over finite fields. Yeah, so but I don't know what else to say about these codes. I don't remember much about them.
Symmetry breaking of SL2R. So is this some kind of in this metric that you found, which is like a deformed SL2R, are some isometries of SL2R still preserved, or you break all the SL2R?
I have not explicitly checked that how much of it would be broken, but it's a good question. It seems to me that definitely ADS2 is not there, and now ADS2 is not there in the bulk. Okay. Now when I'm going to the boundary, maybe some part of it would still survive, but the corrections that we get in the regime of temperature that we are interested in, where these mass gaps were formed, right? There you can show that these corrections are perturbative, but the corrections to the ADS part and to the S part are of the same order. So it is not that I can neglect one with respect to other. So they are there, very much there, and ADS2 is not there. Now how much of ADS2 would survive, that I do not know. I have not done that yet. Yes.
So it's like probably you already mentioned it in the talk, so I missed the first part. So the first, so the calculation that you did was for non-supersymmetric black holes. Is that correct? So if you are able to do this calculation, fundamentally the statement is that for supersymmetric and non-supersymmetric black holes, both the final answer would just be Schwarzian action, but the prefactor changing. Is that the final conclusion?
So for both supersymmetric and non-supersymmetric, it would be a one-dimensional action, which would be a Schwarzian. For supersymmetric case, there would always be a temperature gap coming from the supersymmetric bound of the system. So the problem that we were talking about would not even appear in that case. So since it is there is a mass gap, in other words, nevertheless the result is given by the Schwarzian. For non-supersymmetric case, the result is given by the Schwarzian. In presence of higher derivative corrections also, the result is given by the Schwarzian, but the difference is there is no mass gap, and that's perfectly fine.
Same question I asked you a couple of months back about this relation between the on-shell value of the action will give you the entropy. This is the Gibbons-Hawking. Does that relation continues to hold in your corrected?
Yeah. So the on-shell value of the action with the beta m term, like the mass term taken into account, will give me the entropy. So the usual thermodynamics, the way we do, will work here. But the point is that we can compute the free energy, we can compute the density of states, and then we see that the density of states itself is vanishing. Hence, so the concept of entropy just does not appear in this case. This is what I wanted to say. So the problem that so the point that I thought was a problem 2 months back, I realized right now that that's not a problem. It's just that entropy is not a right quantity to look for such system, but the system is well defined because the density of state smoothly vanishes when I'm going to t to the 0 limit. So system is well defined. It's just that we should not be looking at entropy, rather we should be looking at the density of states. Which is not valid, sorry? So for example, for extremal black holes, that is not true, right? Yeah, so when t goes to 0, entropy doesn't go to 0, but in this case the issue is that as t goes to 0, the density of states also goes to 0. Hence, even the thermodynamic entropy is not the right quantity to look at. That's point 1, but thermodynamics is nevertheless well defined. And the second point is that the t going to 0 limit is smooth. The one issue here is that when we will compute, sorry. Yes, you are right. So t going to 0 limit is going from near extremal to extremal. Yes.
But there we know that there are situations where the entropy is not 0.
Right. Right. So here here I am talking about delta S, which is the difference from the extremal entropy. So that is what is the extremal. Yeah, there is no issue.
Yes.
The corrected metric, if you normalize the radial coordinate to be the r squared over r squared, what would be the second term? Oh, you see, we don't have a blackboard. I want to understand the form of the corrected metric.
Yeah, but you are asking me that I understand. Just give me a minute.
Yes.
First of all, I would like to thank the organizers for organizing this nice conference and also giving me the opportunity to speak here. So the title of my talk is M5 brain prongs, string soliton bound states and their wall crossing. This is the talk based on this particular paper that I put out with Narayan at CMI, and we have another related work which is ongoing with the Narayan student at CMI. Hopefully it will come in this month. So first I would like to speak a few lines on 60 gauge theories. So 6-dimensional 2,0 theories are theories with a self-dual 3-form gauge field strength which have the same degrees of freedom as the world volume theory on an M5 brane. By ADS-CFT correspondence, the non-abelian world volume theory on a stack of large number of M5 brane is conjectured to be holographically dual to the ADS 7 times S4 solution in M theory. In a single M5 world volume, the self-dual strings charged under this field strength capital H are understood to be the fundamental excitations in the theory. Often they are infinite in length and may also be thought of as the lines of M2 branes that end on the M5 brane. So just like n equal to 4 super Young mills, the vacuum of the theory exists in the Coulomb/tensor branch when the M5 branes in this stack are well separated from each other at finite distance, and the associated gauge symmetry becomes abelian. So now the bound solitonic states we are interested in studying in this talk. So a single M2 brane ending on a single M5 brane leads to a half Weber state described by a rich shaped spike deformation of the world volume of the M5 brane with the one transfer scalar getting excited in this particular fashion. So here are the two of the papers from Yes, a straight line along. Along. Yes. So, so these are few of the papers which found these scalar excitations as the classical solutions of the world volume equation of motion. Rho is the rho vector is the distance that we. Rho notation tries to tell us what is our position with respect to the transfers to the line direction. So rho naught will be like location. Yeah, rho naught will be the location. So appropriate combinations of multiple M2 branes give quarter VPS states described by M5 prong deformation with more intricate structure. This with these multiple M2 brane scenario, what will happen? This excitation will no longer be a spike, rich shaped spike, but it will in some way bifurcate so that it has a prong like structure. I will show you a picture.
This is like the analog of PQ string, you know.
Yes, this will exactly become the PQ string excitations when you compactify appropriately on a torus. So, yeah, so these excitations can also be thought of as a superposition of two spikes corresponding to a bound state of two non-parallel string solitons at fixed separations transferred to the extended direction, and which dovetails the non-trivial boundary conditions that we put on the scalars, the vicinity of the string course that I am going to discuss in detail in the coming slides. So under M theory type 2V duality obtained from compactifying M theory on T2 they will reduce to D3 brain prongs as far as I was telling you, representing waves stretched between multiple parallel non-coincident D3 branes, which we are going to now review.
But how can a prong have two spikes? It should be three spikes, right? Three different
Right.
classes will be there. So it should be in a plane.
Yes. Right.
Like a Y. So that will be three, not two.
So okay, let me show you the picture.
Picture I want. Yeah.
So yeah, this is a bound state excitation on the world volume of a D3 brane. So here the kind of prongs like structure I am talking about. So this looks like a prong in the transverse 2D space, which is transverse to the world volume. So and in this way, so yeah, again, let me come to this. Yeah, so this is the plan of this talk. So first I will review the bound solitonic states in the n equal to 4 super Yang mills. Then in the next part, I will going to tell you how the Bogomolny completion is done in order to get the BPS bound equation in the low energy M5 effective field theory. And then I will discuss a particular example of the bound configuration of a pair of string solitons, and then I will end with a conclusion. So now first towards reviewing these bound dionic states in the super Yang mills. So there exist multiple charge course BPS solutions in the super Yang mill theory, which can be stable only in certain regions of moduli space. So such states are solitonic dions with both electric and magnetic charges, and when the moduli parameters associated with such solutions no longer take values in those certain stability regions, these multi-core states decay into two or more simpler core solutions, and such regions of stability are usually separated from the regions of instability by a domain wall or a wall of marginal stability. So snapshot of this decay process of these bound states can be analyzed by changing the moduli values in the field solution. So as one approaches taking values towards the wall of marginal stability, the distance between the centers of the two charge cores, two or more charge cores, I mean here I will only demonstrate with an example of two charge core solution. So center of two charge cores increases, and on the wall of marginal stability they become infinitely separated in a way that distance between the two charge cores is infinitely greater than the radii of the individual cores. So this decay process can also be understood from the D3 brane construction, where world volume spikes at each charge core, which can also be represented in terms of strings carrying appropriate charges and ending at those core locations on the D3 world volume. So yeah, I forgot to, I just want to go back. I just wanted to mention these references which appeared long back ago in the literature, and they all discusses these bound solitonic states, and there are many more references. Due to lack of space, I haven't been able to put them all. So yeah, so coming back to this figure, so this figure shows us the D3 brane construction of the SU3 gauge theory, where we are going to discuss these two-centered charge core configuration. So here these three vertical lines are can be thought of as the world volume of the D3 brane, three D3 branes, separated from each other in this transverse 2D XY moduli space. And using this notation S, I'm going to describe the location of the two charge cores that exist on the world volume. So this figure in this previous slide described a two-centered dionic state with one electric charge core and other one with a magnetic charge core in the SU gauge theory. This first picture is a description in terms of the brane prongs with spikes at respective charge cores. By prongs, I only mean that now there are two spikes which look in some way like a prong structure. So where the three D3 branes are separated in two transverse direction with the position moduli being equal to these three values, set of values. There are two charge cores with an electric charge, magnetic charge respectively on the first D3 brane. So the spike that is coming out, so this spike that is coming out from the first charge core located at the position S1 meets a single spike that coming out of the second D3 brane, and we glue these two spikes at this particular position. These two cores have the same charge, which is the unit electric charge. Similarly, at the position S2, there is another spike which is coming out from the first D3 world volume, and it meets the single spike which comes out from the second D3 brane, and they are glued at this particular location, and both of them has a unit magnetic charge. So sorry, the notation here is a bit messed up. I've taken this picture from a very old paper, so I could not edit it. So the first D3 brane is denoted by 0, 1 and 2, and so these are the locations of the each D3 branes on the transverse moduli space.
Constantly x direction is one charge, y direction is the other charge. So you think of one as electric and the two as this thing, and the bound state is one.
Yeah, so yeah, this is a bound state of an electric charge and a magnetic charge. So this prime is the location where we are gluing the two spikes that are coming from, let's say, the first D3 brane and the second D3 brane. So prime can also be thought of as a cut-off value that we are putting on these spikes that are coming out from the world volume. So essentially, these spikes should be infinitely extended from the direction of the world volume, but we are putting a cutoff, and then we are also gluing these two spikes in this particular way. So moving on from this picture, I would like to show you how the Bogomolny completion of this energy density function of a U1 gauge theory on a single D3 brane is done. So this is how the energy is extremized, and the energy takes the minimal BPS bound value when these two conditions are satisfied, and these equations, along with the classical Euler-Lagrange equation of motion, imply that scalars are harmonic functions, and for a quarter BPS state with one electric and one magnetic charge core, we have these following solutions for the scalars. So now we see what happens to the value of these scalars when we approach the two charge cores. So when we approach the first charge core, we see that x scalar value diverges. So we put a cutoff value on the scalar x1 that we have also seen in this figure. So that x1 can be understood to be equal to this particular notation. And when we approach the second charge core, the y value, so the y scalar value diverges, and we put a cutoff value on this long spike to be a value y1. So now it is then consistent to impose this particular boundary condition on the scalars near the centers of each charge core. So putting this boundary condition is equivalent to fixing the separation distance between the charge cores in this particular way. So mod S1 minus mod S1 bar minus S2 bar is nothing but the separation distance between the two charge cores. And this separation distance becomes is large relative to the core sizes, and in the limit of approaching wall of marginal stability, where x0, y0 value are very smaller cutoff values x1, y1. So as we hit this wall, this x0, y0 moduli vanishes, and these states become arbitrarily loosely bound and they decay from the spectrum. So no bound state exists on the other side of this wall, where moduli value x0 is negative, and more general field configurations with the more number of charge centers can be analyzed in this particular way with a similar reliable behavior near the wall of marginal stability. So now we move on to the bound solitonic states in the 60 gauge theory. So motivated by this by these investigations in the super angles, we consider an abelian M5 field configuration representing VPS bound states of self-dual strings, which had already been anticipated in some way in this review lectures by John Schwartz. So moduli boundary conditions in the vicinity of the string core we impose are Dirichlet boundary conditions on the scalar at the closest point of approach the two strings, which imply fixed separations transverse to the extended directions of the strings. For a generic finite separation, these leads to non-trivial variations in the scalar values as we go far along the strings, which amounts to non-trivial brane bending. So we are going to see, as we are going to move along the length of these strings, these scalar values will vary. They will no longer be constant. So yeah, this remark will become more clear when I show you the pictures which are relevant for these constructions. So however, in the limit of approaching the wall of marginal stability, we show that these variations become negligible and the scalar values become near constant all along the strings. Thus this formulation reveals self-consistent approximate configurations which becomes increasingly accurate near the marginal stability limit, as we are going to see. So BPS bound equations are obtained by performing Bogomolny completion of the low energy M5 brane abelian theory, comprising of a free self-dual 3-form field strength and two transverse scalars. And the expression of this free theory is given by this equation. A Bogomolny completion of this expression can be done, and the minimum bound value for this energy density functional we get is this. Here index A and B are only taking these set of integer values, and this minimum bound is exactly saturated when these two set of BPS conditions are satisfied. So this obtaining this particular equation was one of the main result of a paper. So zeta, I'm coming to tell you about it in the next slide. So these zeta 1 and zeta 2 are some parameters which can be understood as some constant unit vectors for our purpose, and they will have support only in the 2D planar 4-5 subspaces of the 4 dimension of the 5 dimension in the world volume of the M5 brane. These 4-5 dimensions our directions are going to be the directions over which we will assume there's going to be a T2 compactification. So this whole calculation stimulates the intuition that that is what I was going to say. So upon compactifying this 2D subspace as 2, the line charge wrapping the zeta directions, these zeta 1, zeta 2 unit vector directions, become point charges in the remaining non-compact 3 dimensions. So in this slide, these equations can be decomposed into components along 4 and 5 direction, and some of these components then resembles the BPS equations for the D3 brane that we also saw in the review slides.
Better to take the complex combination X plus I because
Right.
in the T2 thing there's a holomorphic condition.
Right.
So instead of writing X square plus Y square, we should write that from Z bar.
Right. So that exercise also we have tried out, and that exercise become relevant for discussing the bound states in the Seiberg-Witten theory. So that that exercise has not been discussed in this paper, but hopefully we will to discuss it in our coming work. So right. So another crucial ingredient in the M5 description is the fact that the scalar field configurations are subject to some line source conditions that we are going to see what they are, which encodes the translation invariance along the strings, which will be reflected in the rich shape picture that also I am going to show. By the way, the picture was there on the main slide, the first slide was a rich spike. So from there only I try to motivate these solutions in some way. So these along with the BPS bound equations, the moduli boundary condition lead us to the spike superposition in the prong field configurations. So the three-form field, for the three-form field strength, what we do is we redefine it by introducing this particular notation H theta in this particular way. So if we do that, this equation of motion also take this particular form. This particular equation, right? No. So these are only these spatial indices. A, P. So so this is in some sense is a Hodge dual operation only in the transverse in the spatial directions. Right. So this classical equation in this form, along with the first set of BPS condition that we saw in this slide, this particular equation, give this expression. And from this particular equation, this long expression in 7 we interpret these line source condition. So these line condition are said in this way because these derivative are have a dot product with the zeta 1 zeta 2 direction in this particular way, and interpreting these equations from this particular equation also leads to harmonicity in 4-dimensional subspace orthogonal to each zeta vectors. So therefore, right. So Lorentz invariance is only broken along the directions of these line vectors.
So the line vector is it because what you chose, you actually said you dualize along this partial direction.
Right.
Unless you put the line source briefly.
I don't understand. So you are saying that by dualize you mean by. So these are this just some definition we are introducing for our convenience, so that our equations look much more less messy.
Kostas, if it helps you, put a T, put a 0 with the epsilon, and put a DE0.
So,
that's what it is.
So actually,
Put the 0 and the 0 on both sides.
Yeah, that's all. On both the terms.
so I just want to.
On both sides, only on the right hand.
Yes.
So that Hodge duality operation in the 6th dimension has already been introduced, assumed. So when I.
And he's also looking at time independent.
Yes, these are sorry, I should have mentioned that. So these are these are static solutions. So again, in these equations, these A and B only take the spatial indices. They don't run over the zero direction. So
Here it seems you probably kind of a magnetic electric split.
right.
When you do that also in 4 dimensions, so that also breaks matrix invariance. Of course, the equation is still invariant. But maybe doing the analog of that here.
Right. So this electric and magnetic, sorry. So this electric magnetic, by electric magnetic, at this particular point, these are just labels, x4 and x5 directions. At this 60 level, they don't have much value because of since these strings are self-dual. So these extensions along these x4 are x5 direction. We are labeling them as electric and magnetic.
Because eventually, if you rectify an T2, it becomes this.
Right. That is the understanding what we have currently.
How do you get, why is this theory available? Is it coming from some
185?
Yeah, right. So yeah, this is just energy function for 1m5 brain excitations.
That's the field considered with XY.
Yes. Yeah, sorry, I've already introduced that H tilde notation here only, but I thought it would be much appropriate to introduce this notation here, because I was also modifying these classical equations. So, right. So these are the solutions for the scalars x and y, which are harmonic form in the 4-dimensional subspaces transverse to these to these unit vectors zeta 1 and zeta 2 respectively. So I should say that the example I am going to discuss in this talk, only for that particular example, these zeta 1 and zeta 2 will be extended along the x4 axis and x5 direction. They can have arbitrary orientation on the x4 x5 plane. We also do that in the paper.
uniform gauge theory. There are puzzles.
Because I thought there was this two bundles of which you could define speech.
The germs, the
No,
germs.
I thought it was developed now.
Well, I don't know how far.
Sati and Schleimer.
Yeah, how useful that is, I don't know.
So even even in the case of multiple M5 brains, when we look at the vacuum of this theory, we always assume them to be Higgs, so that these M5 brains are separated from each other.
That's what he said, separated that U1
Yeah, so the gauge group essentially becomes U1 raised to power some n. So yeah. Now in this slide, I try to tell you that how these expressions, these BPS equations are related to the BPS equations that we saw in the Yang-Mills story.
Is there any relation to this solutions having certain students around this other 4 or 5 listed? It's in my recollection, it's all the same problem.
Right.
I don't remember whether it's exactly the same here.
Can you please repeat?
It's Henningsen and his students at domains.
Helix.
Henningsen.
Henningsen. Right.
strings that will be the decreased story.
Well, then of course you multiply down to multiple 4 dimensions. And this shall be something
At this point, I don't have much to say.
I don't remember whether it has bions.
There is some paper, not by KM Lee.
This should the paper by Henningsen was about 2003, 4, 5. There was a series of papers.
Maybe I'll try to tell you more afterwards.
So these solutions will not be seeable from this EVGM types. These are all
Right.
So you will really need from the world volume you can only see from M5.
Right. Yeah. If in the ABGM story we have to realign our point of view and should be looking from the M2 brain point of view. So I will try to make connection with the BPS equations in the D3 brain story. So in order to do that, I need to define these notations, capital E, B and pi. These first two notation, E and B, are akin to the electric and magnetic field vectors that we know in the 4-dimensional gauge theory. And in terms of these definitions, our BPS equations in the component form look like this. I just put them because to show how they drastically simplify when we define these auxiliary parameters x prime, y prime in terms of our original scalar fields in this particular way. So BPS these BPS equations take these much simpler form, and obtaining these first two BPS equations in this form is well motivated towards making connection with the ones that we saw during the string web analysis in the n equal to 4 super Yang-Mills review. So before going to the example, to the main example of a bound state, let's first consider a single self-dual string soliton solution of the equations we presented. stretched, which are going to be stretched along x4 direction, so that the zeta unit vector is equal to this. So field configuration is given by this first line. BPS equation are given by these second line, and the expression specify the fact that the x is harmonic in the 4-dimensional subspace transfers to the x4 direction zeta 1 that the string stretches along. We see that there's a divergence in the value of x scalar at the location of the string, which we parameterize using this notation rho bar x comma 0. And this is due to the ending of an M2 brane that extend along the x4 direction on the world volume. This means that there's a spike on the M5 world volume shaped like a ridge with a flat ridge top stretching along the x4 direction. So using this figure, I try to depict the whole picture. So yeah, for this single excitation, this ridge has a flat top. So what we do now is we impose a boundary condition on the scalar when we are very close to the location of the string, and this represent setting up a long distance cutoff in the x space transfers to the M5 world volume, which translates to putting a short distance cutoff around a string soliton core. So by putting the cutoff in the x transfer space also means that we are also controlling the size of the cross-sectional size of the string soliton core. And now this spike in the x space transverse direction is of finite length. So thus the cross-sectional size or the thickness of the string core is given by the inverse length of the M5 spike in the transverse moduli space. So now I will come to the example of the main example in the talk of this of a bound state of two string solitons. So this whole picture is a picture in 7 dimensions. 2 dimensions which are transversed to the world volume of the M5, and in the remaining 5 world volume directions, 2 other directions along which these strings stretches along. So here we have 2 types of M5 ridge shaped spike deformation, where x and y scalar gets excited in this particular fashion, and these are also the transverse direction. These also tell us about what is happening in the transverse direction, x and y.
So you're going to connect them in a smooth way to get the other guy.
Yes. Yeah, this is roughly the idea, but there are some subtleties. Yeah. So this picture is going to stay only at the wall of marginal stability limit. When we are moving, no, it actually, yeah. Yeah, I don't know when, but yeah, we can say with confidence that these 2 rich pictures are going to be true at the wall of marginal stability. Beyond that,
far away from the intersection point also it will look, right? If you go very, very far away.
Right.
If you go in such infinity, you can see these 2, right?
Right.
And that third guy also. One of them you will see at that angle 45.
That's true, but so we have very less understanding about the interaction of these strings themselves. So, right. Maybe I'll.
So what is this omega deformation of necrosome? I mean, this x1 cutoff.
Right.
In terms of this.
Right. Right. So omega deformation of Nekrasov becomes relevant for the Seiberg-Witten theory.
The whole point here is that it regulates certain things.
Right.
Point is it should regulate.
Yeah, it. Okay, I move on. So yeah, so this whole picture is in 7 dimensions. Since we cannot have a picture of that, I tried to split this whole picture into these 4 sub pictures. So A, B, C, and D. So A, B you have already seen. C picture is completely inside the world volume of the M5. So X4, X5 directions are again the directions along which the strings are going to be stretching. Here, this R notation denotes the radial direction in the 3 spaces which are transversed to this X4, X5 plane. And right. So this D picture, this picture D shows the spike in the transverse XY space direction of the M5 prong, which is stretching from the world volume of the M5 that is located at these points minus x0, minus phi naught. So yeah, so now for these bound state, for this bound state, the picture looks like this. So it's no longer a spike, rich shaped spike that we saw when we had just a single string soliton, but now it has become pronged in this particular way. And in the limit of approaching wall of marginal stability, we always think that this x0 minus y naught point is very near towards the origin.
What is this point minus y?
This is the moduli location of the M5 brane. No, this is the location of the M5 brane itself. Yeah.
I thought it's inside the world volume of the M5.
No, this D picture, C picture is inside the D picture is completely inside the transverse XY directions. So the 2D space that is transverse to the world volume. Sorry if I have not been clear enough. Yeah. So this is these are the directions of the scalars actually, the 2 scalars. So now we describe the field configurations given by the 2 scalars on a single M5 brane. Oh, yeah, I will rush. So, yeah, I'll speed up. So, imposing boundary condition on the scalars in the vicinity of the soliton cores ensures that the resulting configuration is a molecule-like bound state of 2 non-parallel string soliton with the fixed transverse separation along the R direction, as we are going to see. So intuition for this boundary condition arises from string web states in n equal to 4 superangles review, and using this table we try to also show how this orientation look like. So in the D3 effective field theory, this is described as a bound state representing a 1,1 charge molecule with constituent charges 1, 0 and 0, 1. And we have solitonic string stretched along x4, x5 directions, but separated along this R bar direction, as we also saw in figure C. And zeta vectors and string yes, zeta vectors are in the 5 brane volume and in the x4, x5 plane. So without loss of generality, we have taken these strings to lie along the x4, x5 direction. And this system, this particular system is described by this particular field configuration. So BPS equation for this setup, for this example, becomes this. And now I'm just going to speed up, sorry about that. So okay, so if we look at the value of the scalars very far away from the two strings, the value of the scalars relax to the moduli value of the M5 brane itself, which is also the location of the M5 in the transverse XY directions. And we are going to see how these X and Y scalar behave when we approach the two string cores. So naturally, when we approach towards the first string core, the X scalar becomes divergent. The value of the X scalar becomes divergent. So this spike is actually is of infinite length. And what we do is we put a cutoff on the value of this X scalar, whereas Y scalar remains non-divergent. And we slightly analyze how the value of this Y scalar changes as we move along the first string. So when we are at a very large distance from the origin on the first string, this Y scalar relaxes to the moduli value minus Y naught, whereas at the origin, the value of the Y scalar is this. Similarly, when we approach the second string, the Y scalar is the one which is getting divergent, and the spike is of infinite length. So we put a cutoff on the value of Y scalar to be Y1, and then so X scalar remains non-divergent. So we analyze slightly how the X scalar value behaves when we are moving along the string. So at infinity, the value of the X scalar relaxes to the moduli value minus X naught of the M5 brane, and at the origin, the X scalar is of this particular value. So from similar bound state configuration arising from D3 brane prongs, we know that the separation between the constituent charge cores is fixed and scales as the inverse distance from the wall of marginal stability. Using this intuition, we impose this particular constraint, which looks very similar to the constraint we also put in the D3 brane story. So imposing this constraint is equivalent to imposing these two boundary conditions at the location of the two string, and we are only imposing this boundary condition only at single point on the string, not all along the string. So at the origin point of the first string, we are putting this boundary condition, and at the origin point of the second string, we are putting this boundary condition. So equivalently, these conditions can also be thought of as fixing the transfer separation between the two strings. And here I tabulated how these scalar values are changing as we are moving along the two strings. This also supposed to suggest how by what I meant when I said the non-trivial brane bending in the earlier slide. So I'll skip this point. So we see that as the wall of marginal stability is approached, the separation distance again diverges, and while their core cross-sectional size remains finite, so alpha I inverse is so alpha 1 inverse and alpha 2 inverse are the sizes of the two strings, and thus near this marginal stability limit, the bound state decays from the spectrum. So I had a few slides on discussing the effective tension formula, which I don't think I will be able to. So I just I just want to explain this particular slide a bit, how we are going to embed this M5 brain prong picture in the Higgs theory of 3 parallel M5 brains. So here is the picture, very similar to the picture that I show for the D3 brain story. So here we have now 3 M5 brains separated in the 2 transverse XY direction. The first M5 brain has 2 soliton strings on its world volume, whereas the other 2 have only single solitonic strings. From the first world volume emerges a prong-like deformation. What we do is we glue the first leg of the prong with the M2 brain that is going to emerge from the string soliton on the second M5 brain, and we glue the second leg of the prong with the M2 brain that is going to emerge from the string soliton on the third M5 brain. And in the limit of wall of marginal stability, the position of this first M5 brain is going to be very close to the origin in the transverse XY direction in comparison to the other M5 brains. So now I'll conclude quickly. So we have constructed and described field configurations representing self-dual string soliton bound state in the M5 brain effective field theory. The bound state of 2 string solitons described by M5 brain deformations have non-vanishing fields and components sourced by 2 scalar fields. To describe the bound state of string soliton state, operationally wrote down the solutions to the BPS equation that describe a superposition of 2 non-parallel solitons, where we looked at the simplest possible example of 2 orthogonal strings. We then imposed boundary condition describing the scalar moduli values as we approach the string relation. These are imposed at the closest point of approach of 2 strings. This is equivalent to fixing the separation distance between the strings transverse to the extended direction in terms of the distance from the wall of marginal stability, which gives the separation distance between the 2 strings towards going to infinity at the wall of marginal stability limit. So in the outlook, instead of following the above, one could also impose a boundary condition that amount to holding the strings fixed far along them at infinity. So now in this particular picture, we put the boundary condition at the origin points when the 2 strings were so the closest point of approach of 2 strings, that was the origin. One can also think of putting this boundary condition at the infinity, far at the infinity, and then allowing the rest of the 2 string geometry to be determined by the energetics. In this case, the scalar configuration will be different from what we saw, leading to brain bending that reflect in 2 strings deformed towards each other in the near regions. One could also imagine more general configurations with such as 3 or more M2 brains sitting on the M5 brain, which may relate to the D3 brain prong configuration pertaining to 3 or more charge centers, as was also studied in these papers. One can also consider this setup in a more suitable way for the n equal to 2 Sarthak-Witten theory, where half of the supersymmetry are broken under a twisted compactification on a T2 torus, and a decay process of the W boson state there can be reproduced near the wall of marginal stability. This is what we are trying to do currently. This method for bound string soliton states may also be useful to study other extended operators in gauge theories, like surface operators, where a discussion of 2 or more of them intersecting forming junctions has also appeared in the literature. Thank you. Sorry if I have ran over.
Thank you. No. Actually, it's not your fault. Apparently there's some other meeting at 6 o'clock. Okay. So we have to keep time. Really sorry about that. Okay. So we have time for 1 or 2 quick questions or comments.
I don't know, you have time to explain what is the decay of W boson process in this case?
Yes. So
effective field change, you still have some massive W boson.
Right. But the mass of the states in the spectrum changes as you vary on this U plane in the Seiberg-Witten description.
How does the decay happen? The same thing. Mechanism is similar.
Yeah, that is what.
Okay, so
Thank you.
thank you, Varun.
Thank you.
We thank him again. So tomorrow we start at 9:30. So see you here.